Should I test it? Test.
It'll test when you're done now.
Got you. Yep.
Okay, yeah. And I'll turn it off.
Just leave it on, and he'll unmute you when it's time to speak. It's muted right now.
Oh, it's muted.
Okay, so welcome to the third session. We're going to have three speakers over the course of the next hour and a half. Two astrophysicists / physicists and then a historian philosopher of science. And just again, if you don't mind keeping your questions until the end of the talk, that would be great. Thank you. So our first speaker in this session is Professor Amy Rines from Montana State University. She's an astrophysicist and works on a variety of aspects of supermassive black holes and on star formation. And today she'll tell us about local relics of supermassive black hole seeds in dwarf galaxies.
Great, thank you. Right, so today I am going to talk about searching for these massive black holes in little dwarf galaxies and how these objects can impact our understanding of the origin of the first black hole seeds. Now, in the local universe, we know that massive black holes are typically found in giant spiral and elliptical galaxies, and these black holes are very important to many different areas of research in astrophysics, including galaxy evolution, gravitational waves, of course, active galactic nuclei, the epoch of reionization, tidal disruption events, and others. But we don't know how these black holes get started in the first place. As we heard from Priya earlier, the seeds may have been remnants from the very first generation of massive stars, or maybe they were formed from the direct collapse of dense gas in the early universe. There are other possible seed formation mechanisms. For example, you could have these collisions in star clusters that could produce black hole seeds of sort of intermediate mass. Now, unfortunately, directly observing these first seed black holes in the earlier universe is currently not feasible. The black holes that we do detect in these very high redshift quasars are already quite hefty with typical masses of 10 to the 8 to 10 to the 9 solar masses. Various studies have looked for AGN signatures in early galaxies where the black holes are expected to be much smaller, but they're not robustly detected even in the deepest X-ray observations. Fortunately, present-day dwarf galaxies, small galaxies, offer us another avenue to learn about the origin of these supermassive black holes because these low-mass galaxies basically can host local relics of the first black hole seeds. So we know that in general, bigger galaxies have bigger black holes. So if you want to learn something about black hole origins, it makes sense to look in these low mass or dwarf galaxies. Unlike today's massive galaxies that have black holes that have already grown substantially through accretion and mergers, dwarf galaxies that have experienced relatively quiet merger histories are expected to host black holes that are relatively pristine. And indeed, models of black hole growth in a cosmological context, starting with different seeding scenarios, do predict that the observational signatures indicative of the seed formation are strongest in today's dwarf galaxies. And so the primary diagnostics that people talk about include the black hole occupation fraction, which is shown on the left here. This is simply the fraction of galaxies of a certain mass or velocity dispersion that contain a massive black hole at all. And other diagnostics include black hole host galaxy scaling relations at low masses. So hopefully you can see in these plots things look different at the low mass end. That's where the power for distinguishing between these models lies. Okay, so I think there's clear motivation for searching for and studying massive black holes in these nearby dwarf galaxies. This really is our best observational probe of the origin of black hole seeds, at least with current facilities. In general, just finding the smallest black holes really places the most concrete limits on the masses of black hole seeds. Now, in general, the most secure method for discovering these black holes is to use stellar or gas dynamics to weigh the central black hole. And while there are a few detections and a few upper limits in some nearby dwarf galaxies, the gravitational sphere of influence can't be resolved for low-mass galaxies that have small black holes when these galaxies are at distances much beyond the local group, at least with current facilities again. So we really are kind of forced to search for these black holes that are active, that are shining as active galactic nuclei or AGNs in these more distant dwarf galaxies. Now, AGNs in dwarf galaxies are quite challenging to find. First, we need to appreciate that AGNs in dwarf galaxies are powered by smaller black holes than typical AGNs in more massive galaxies. Therefore, these AGNs are going to be less luminous at a given Eddington fraction. Just as an example, the Eddington luminosity of a 10 to the 5 solar mass black hole is only about 10 to the 43 ergs per second, but that's the luminosity if it's accreting at a very, very high rate, and we know that black holes with high accretion rates are relatively rare, so the actual luminosities of these AGNs could be orders of magnitude lower. So you really have to lower your threshold for what might be an AGN in a dwarf galaxy, but then at the same time, you also need to be aware of possible contamination from star formation-related emission. So these lower mass dwarf galaxies tend to be star forming on the whole, so we really have to be cautious when we are trying to identify massive black holes in these dwarfs. Okay, so with all of this in mind, I now want to tell you about some multi-wavelength searches for AGNs in dwarf galaxies, and I'm going to review some of my previous work and then also tell you about a new survey that I'm working on now that I'm really excited about. Okay, so optical spectroscopy has so far produced the largest samples of dwarf galaxies hosting massive black holes. For this study, I analyzed the spectra of about 25,000 dwarf emission line galaxies in the Sloan Digital Sky Survey, and all of these galaxies have stellar masses less than or equal to 3 billion solar masses. And this mass threshold for what I'm calling a dwarf galaxy is equal to the stellar mass of the Large Magellanic Cloud, which is the largest dwarf satellite galaxy of our own Milky Way galaxy. So I searched for photoionization signatures of accreting black holes using narrow emission line diagnostic diagrams, such as this one here. This is called the BPT diagram, after the authors that presented it at first. And then I also searched the spectra for broad H-alpha emission that could signify dense gas orbiting around a black hole. And for these, I can actually use the broadline kinematics to get an estimate of the black hole mass. So just very briefly, the mass of the black hole just goes as RV squared over G, and the average gas velocity comes from the width of this broadened emission line. In this case, I'm using H-alpha because it tends to be bright. And the AGN luminosity is used as a proxy for the radius of the broadline region where that gas is coming from. And this is based on the radius luminosity relationship that's been determined for a subset of AGN called reverberation mapped AGN, in which the size of this broadline region is determined from the time lag between variability in the continuum and a broad emission line. Okay, so that's how we get black hole mass estimates from spectroscopy. And here are the main results. So based on the narrow emission line ratios, I found 35 AGNs and 101 objects falling in this AGN star-forming composite region, which also likely host massive black holes. This was a major step forward. Before this study, there were only a few galaxies in this mass range found to host massive black holes. I'll also note that the least massive galaxy in this sample has a stellar mass of just a few times 10 to the 8 solar masses, so this is about the mass of the Small Magellanic Cloud. On the right, I'm only showing the broadline AGN candidates. So 10 of those AGNs in composite galaxies had broad H-alpha in their spectra, and additionally, some dwarf galaxies with narrow line ratios falling in the star-forming part of the diagram also had broad H-alpha emission. This is the distribution of those black hole masses for the broadline objects. The 10 broadline objects in the AGN and composite region are shown in this orange histogram, and the median black hole mass for these is just 2 times 10 to the 5 solar masses. These are among the smallest supermassive black holes known, and the masses are even overlapping with masses predicted by some of these seed formation models. Vivian Baldassari, and she's an Einstein Fellow at Yale right now, she has used our follow-up observations with Chandra to confirm that these are indeed AGNs. They have high X-ray luminosities. And we also have new HST observations of these dwarf galaxies, and my student, Zach Shetty at Montana State, has used these data to populate the low mass end of the black hole bulge mass relation, which has been submitted and should be out relatively soon. Okay, so now these objects with broad H alpha falling in the star-forming part of the diagnostic diagram are shown in blue. And I was suspicious of these objects because they didn't have the narrow line ratios indicating photoionization by an AGN, and the broad lines tended to be really broad, leading to these abnormally high black hole masses that you can see here compared to the more secure broadline AGNs in that orange histogram. And indeed, our follow-up spectroscopy indicates that the broad emission just in these star-forming objects is likely from type 2 supernovae, not AGNs. So broad H alpha alone should not be taken as conclusive evidence for an AGN, at least in this low mass regime, possibly at higher masses too, I'm not sure. But you really want these narrow line ratios indicating an AGN too. In this follow-up work, we also discovered a new broadline AGN in my SDSS sample with a black hole mass estimate of just 50,000 solar masses. This relatively tiny black hole lives at the center of this dwarf galaxy here, which was originally classified as a composite object in my SDSS sample, but I didn't have any estimate for the black hole mass because the broad line fell below the detection limit from that original SDSS spectrum, but we got better data, higher resolution spectroscopy, which is shown here, and you can really now detect robustly this broad H alpha line and get a black hole mass, and it's tiny. Okay, so while these spectroscopic searches for black holes and dwarf galaxies have been quite fruitful, these optically selected AGNs are likely just the very tip of the iceberg. This selection technique is only going to be sensitive to the most actively accreting black holes in those galaxies with relatively low star formation. So we really need to start using other diagnostics. And so one other way that I'm searching for massive black holes in dwarfs is using high-resolution radio observations from the Very Large Array and X-ray observations from Chandra. And so these observations can actually reveal black holes that are missed at optical wavelengths. Compact radio and X-ray emission at the center of a galaxy is generally a good indicator of accretion onto a massive black hole, and the high angular resolution, particularly with these telescopes here, allows you to separate any compact emission from the host galaxy. And we have a really nice example of how this can work. So the combination of radio and X-ray observations has provided a strong case for a massive black hole in this dwarf starburst galaxy called Henneis 210, despite the fact that optical emission lines, at least from ground-based spectroscopy, are just dominated by the starburst in this system. And this discovery really marked a whole new environment for a massive black hole, and I was motivated to look for more objects like this using radio and X-ray observations. So far, I've also discovered a candidate massive black hole in this low metallicity dwarf galaxy pair called Markarian 709. We're also doing what we can with archival data, and we have a number of X-ray detected candidate black holes from the Chandra archive. And I'm also working on a new radio survey, which I'm excited to get to tell you about today. Hopefully this will be done relatively soon. Okay, so I designed this survey basically to conduct the first large-scale radio search for massive black holes in dwarf galaxies, and this is going to help with our understanding of black hole demographics at low masses because these radio observations probe a different parameter space than the optical selection. In general, these observations are more sensitive to lower black hole accretion rates and black holes that happen to be living in star-forming host galaxies. So I obtained VLA observations of 111 dwarf galaxies. These all have stellar masses, less than 3 × 10⁹ again. They're all relatively nearby. And in order to maximize the number of detections and to target galaxies with radioluminosities similar to Henneis 210, I selected dwarf galaxies in the SDSS that were also detected in the first radio sky survey. So FIRST stands for faint images of the radio sky at 20 centimeters. So it's an existing sky survey at 1.4 gigahertz with an angular resolution of about 5 arcseconds and a detection threshold of about a millijansky. So my new VLA observations have a much higher angular resolution, and they're also much deeper. And this is really important because the compact emission from an AGN, which is what I'm looking for, can be just a tiny fraction of the total radio emission on larger scales. So I observed my target dwarf galaxies in the most extended A configuration, which gives the highest spatial resolution. The observations were taken at about 10 gigahertz, and these observing parameters yield a resolution of about 1/4 of an arcsecond. So the beam solid angle is about 400 times smaller than the first survey, and the RMS noise is about 15 microjanskis per beam, so these observations are about 10 times more sensitive than first. Okay, so I'm going to skip over all the details and just show you some results. So this is a plot of the 1.4 gigahertz luminosity from first versus stellar mass for my whole sample. And so you can see that all of my target galaxies have stellar masses similar to or less than the LMC. All of the 111 dwarf galaxies that I observed with the VLA are shown in purple, and I detected compact radio sources in 39 of these galaxies, and those are the ones that have orange circles around them. So I have about a 35% detection rate, which is not too bad. Here are the compact radio sources detected with my new VLA observations. So the VLA images shown here are only 4 arcseconds on a side. Many of these detections are consistent with being point sources. And so I detected a bunch of these sources that could be due to accreting massive black holes, where we're seeing synchrotron emission from a compact jet or something like that. However, at radio wavelengths, especially in this luminosity regime, I also need to consider alternative origins for the radio emission and see if I can start ruling some of these things out. So I'm not going to go into the details here, but I've considered various possible origins for this compact radio emission, including thermal H2 regions that are just associated with extragalactic young massive star clusters. I've considered supernova remnants and younger radio supernovae, as well as populations of these objects, and then of course AGNs, which would signify the presence of an accreting massive black hole. And my analysis demonstrates that AGNs are almost certainly responsible for the compact radio emission in at least 14 of my target dwarf galaxies, and there are other candidates as well. So here are the optical images of these 14 dwarf galaxies with very luminous compact radio sources. These little red crosses indicate the positions of the compact radio sources, and the circles indicate the position of the SDSS spectroscopic fiber if there is a spectrum. And I realize these crosses are difficult to see, so let me blow them up a little bit. And hopefully you will notice that some of these are not at the center of their host galaxy, okay? And when I first saw this, I was very surprised because this hasn't been seen before. All of the black holes that are found in dwarf galaxies previously have been located in galaxy nuclei, okay? However, recent simulations predict that roughly half of all massive black holes in dwarf galaxies should be off-nuclear, wandering around in the outskirts of their host galaxies just due to the shallower potential wells of these dwarfs. Okay, so what could cause at least some of these black holes to be off-nuclear? Well, you could get off-nuclear black holes from tidal stripping during a dwarf-dwarf merger, where at least one of the progenitors had a massive black hole. Alternatively, you could get an off-nuclear black hole as the result of gravitational radiation recoil during the coalescence of 2 black holes brought in, I guess, by a merger. Of course, the merger of these black holes would produce gravitational waves and cause that merged black hole to get a velocity kick and spatial displacement. And we heard a little bit about this, that these gravitational waves from massive black hole mergers in dwarfs will be hopefully detectable with LISA. That's what we're expecting to find. Now, I do need to put out a disclaimer here, and that is that I really want to caution that I have not yet assessed possible contamination from background AGNs that could just happen to line up with some of these dwarf galaxies, although I don't think that's going to account for all of these. Okay, so if these radio sources are indeed associated with these dwarf galaxies, this is really exciting because until now there just hasn't been compelling evidence for off-nuclear black holes in these systems, despite predictions from simulations where you expect to have some of these wandering black holes not living in the center of their galaxies. Moreover, for those of us that do this for a living, if we want a more complete census of massive black holes in dwarfs to help constrain seed formation, our searches need to account for such a population of these wandering black holes that are not necessarily nuclear. Okay, so now I want to come back to something that I mentioned earlier. I'm switching gears a little bit, and I want to draw some connections to the high-redshift universe. And I think I mentioned briefly that AGNs have not been detected in very high redshift galaxies, okay? And this has been a little bit of a puzzle, and so I want to talk about that. So first of all, these high redshift galaxies have stellar masses that are similar to the dwarf galaxies that I'm studying locally, where we are finding these AGNs. So we expect these early galaxies also should have already been seeded with a black hole. Okay, so we think these early galaxies have black holes, but they haven't been detected. Now, if you assume the local black hole bulge mass relation holds at these high redshifts, and you assume that total stellar mass is a good proxy for bulge mass, you'd expect these early galaxies to host relatively massive black holes, around 10 to the 6 solar masses or so, and at least a few of these should be luminous enough to be detected using deep X-ray observations that we have, but they're not robustly detected either individually or using stacking techniques. Now, at the distance of these galaxies, you can't estimate a bulge mass. You're only going to be estimating a total stellar mass at best, and it's not clear that these low-mass, high-redshift galaxies even have well-developed bulges at this very early stage of galaxy evolution, so maybe the black hole bulge mass relation doesn't actually apply at all. So Marta Voluntari and I investigated how the scaling between black hole mass and total galaxy stellar mass in the local universe impacts this interpretation of the lack of AGN detections in these high redshift galaxies, where we think they should have at least some detectable AGNs. So I'm, again, skipping over all the details of the work that went into this, but this is my plot of black hole mass versus total galaxy stellar mass for 341 nearby galaxies. I think you will agree there is a lot of scatter here, but in general, ellipticals and bulge-dominated systems, mostly at higher masses, live in this region here. These are the systems that have dynamical black hole masses and define the black hole bulge mass relations, which I'm also showing here as these gray lines. Now, local broadline AGNs, including the dwarfs that I've been talking about, fall about an order of magnitude lower in this plot. And so if this lower mass AGN relation holds in these high redshift galaxies, we'd expect the black holes to be about 10 to the 5 solar masses rather than 10 to the 6 solar masses if you had assumed the black hole bulge mass relation holds. The AGNs would therefore be less luminous, and as shown in this companion paper led by Marta, our relation between black hole mass and total stellar mass can actually explain the current non-detections of AGNs in these high redshift galaxies. So these high redshift galaxies may and very likely do host massive black holes, but it's quite possible they're just less massive than people have thought, and they're just falling below the detection limits. But we don't need to invoke any weird exotic scenarios to explain the non-detections. And we need to basically wait for the next generation of observatories to find and study black holes in these higher redshift low mass galaxies. There is some hope with James Webb, and you can see these references here for more on that. Okay, so let me just give you my quick take-home points. So first of all, contrary to conventional wisdom, dwarf galaxies can, and at least some do, have massive black holes in them. Moreover, the population and properties of black holes in nearby dwarf galaxies hold clues to the formation of the first seed black holes in the early universe. Using optical spectroscopy, I've increased the number of dwarf galaxies known to host massive black holes by more than an order of magnitude, and I have a bunch of new exciting candidates from this radio survey. We're finding some of the smallest black holes known in galaxy nuclei, and we're starting to really push down into this intermediate mass regime. And just a word of caution that identifying black holes in dwarfs is challenging. At these low luminosities, you do need to be aware of possible contamination from all sorts of stellar processes, including starbursts, supernovae, X-ray binaries, all this kind of stuff. And then finally, our scaling between black hole mass and total stellar mass for local AGNs can explain the current lack of AGN detections in high redshift low mass galaxies. And I will stop there. Thanks. Okay, thanks.
Okay, questions?
One aspect that is a bit worrisome about identifying these off-center radio sources in the dwarf galaxies as black holes is the fact that, at least in the nuclei of galaxies, black holes shine for only 1% of the Hubble time in the present-day universe. For a short fraction of the age of the universe, they have a limited fuel reservoir. And so if they get kicked by some mechanism out of the center, they would even have less fuel supply. So they would basically carry at best the accretion disk that they had before they were kicked. And one would not expect that to last more than 10 to the 7 years in fueling them. So what's your thinking about how can you maintain this radio, or which fraction of your dwarf galaxies have those?
It's very low, so it's going to be well under 1% or less, because I first pre-selected things in Sloan, at low mass galaxies in Sloan that were detected in first, and even that selection was very low, less than 1%. And then I only detected, a third of those, and then half of those or something are even less. So it is a small fraction, so it doesn't seem to be a super common thing, although, again, this is a very biased sample, so it's hard to really say anything conclusive about the demographics.
So I was wondering, this method that you're using to measure masses, which is from just one spectrum, looking at the spectral line, width,
Right.
and luminosity, etc. So if you were to put kind of honest uncertainties, systematic errors, and especially the modeling errors, like the luminosity radius relation, which is completely empirical. So if you fold that all in, what do you think is a reasonable uncertainty on each of those mass measurements?
Probably a factor of 3-ish, I think is.
3 either way?
Yeah, I think so, roughly speaking. Yeah, so it's not great, but it's the only thing
It's
we
the only
can
game in
do.
town. Yeah, I know.
Yeah.
So I'm curious about the details of how you're doing your classification of the radio sources. Are you only using the radio emission, or are you using other multi-wavelength
Using
tracers?
other things. So I do have some plots I can show. So this is, okay, so let's see. This is showing okay, so you have this radio emission. If I assume that it's thermal emission from star formation, just ionized gas, then I can estimate an instantaneous star formation rate of that little region. Then I go and I can estimate the star formation rate of the entire galaxy using Galax and WISE data, so dust corrected. And that's what I'm plotting on the x-axis, right? So basically, the line is showing the 1-to-1 relation, so any point that lies above that line basically should not be allowed to exist as an H2 region because it would have a star formation rate higher than the entire galaxy. Okay, so that's one thing. Then I can also show, this is the luminosity, the radioluminosity versus star formation rate again, where the line is showing a relationship between the luminosity of the brightest supernova remnant or supernova in a galaxy as a function of its star formation rate. So that's where things live. So supernova remnants should live below this line. None of them do. I'm not showing it here, but I've also figured out if a population of supernovae or supernova remnants could account for the luminosity, and some of them, it looks very similar to the other plot actually. So all of the points that fall above these lines on all of these plots basically are too luminous to be star formation related things. So that's generally how I'm doing it.
Any further questions? Okay, perhaps we can thank Amy once again. Thank you. Okay, so our second speaker in this session is Professor Manuel Berti from Johns Hopkins. He's a theoretical physicist who specializes in gravitational physics and gravitational wave astronomy. And today he is going to be telling us about, if I have the title right, hopefully, physics and astrophysics with low-frequency gravitational waves from black hole binaries.
Thanks. I am actually classified as an astronomer on the.
You're right upstairs.
Yeah. But I'm a gravitational wave astronomer, so I'll take it. Okay. Well, you heard from Michael's talk this morning that LIGO has been doing some amazing things. During the first two observing runs, we had 3 binary black holes in the about, 4 months of O1, and then 7 binary black holes and a binary neutron star during O2. What you see over here in this plot is the range for binary neutron stars of the 3 LIGO detectors during those 2 runs. And as you can see, they've been getting better and better over time. And now, now that we are in the era of open data, even people who are not in the LIGO collaboration know more or less what's going on. And the status of the detectors is available online, and that is indicative of how far we can see things. And we have already a number of public alerts that include, according to the last conversation that I had over lunch, 8 binary black holes, 2 binary neutron stars, and 1 neutron star black hole. But I promised myself that I will never put up a slide like this again, because if you look at the last alerts, there was about 1 every 2 days in the last 10 days. And so I'm giving up on trying to stay updated on the status of gravitational wave observations. And of course, all of the binary black holes, this is a conference about black holes, all of the binary black holes that have been observed by LIGO are in the stellar mass regime. And at the other end of the spectrum, we had this beautiful image from the Event Horizon Telescope collaboration of a black hole at the center of M87. And how do we bridge this gap? Most of my talk is going to focus on space-based gravitational wave astronomy and the promise of space-based gravitational wave astronomy to do black hole astrophysics. Now, for those of you who don't work in this field, the main number to keep in mind is that if you take 2 black holes of equal mass and you merge them together, you get a final black hole that rings down with a certain characteristic frequency, and that frequency is 170 hertz for a black hole of 100 solar masses, and then you can scale it up or down. So this means that if you take a black hole like GW150914, more or less, it's pretty much in the bucket of the LIGO frequency, of the LIGO power spectral density. And if you scale this down to a black hole of about 10 to the 6 solar masses, then you would have a ring down frequency that is right in the bucket of the LISA sensitivity window. Now, the second thing that you need to keep in mind is, besides the frequency, the amplitude of these waves. And it's a very easy calculation to show that the signal-to-noise ratio for the ring down from 2 black holes scales with the power m to the 3/2 of the mass of the black hole. So if I go down by about 4 orders of magnitude in frequency, I go up by about 6 orders of magnitude in amplitude. And this means that typically for binary black hole mergers observed in LISA, I should expect signal-to-noise ratios that are very large. And to go to signal-to-noise ratios that are comparable to what I can expect with LISA, I need to improve Earth-based detectors to a level that corresponds more or less to to the detectors that you see in green and blue here. These are called third-generation detectors, and in Europe there's a proposal for something called the Einstein telescope, and in the US there's something called Cosmic Explorer, but in the end these are going to be big international collaborations, and we will see what happens. Now, in LISA, there are three key sources that we'll discuss. Just to give an idea of the structure of this talk, first of all, in the first half, I'm going to be a little more conservative, and I will talk about the astrophysics of these sources. In the second half of the talk, I'm going to be more of a theoretical physicist, and I will talk about some of the interesting things that we could learn if more exotic physics is at play. So, the three classes of sources I will focus on are massive black holes. What you see here are three typical tracks of in-spiral, merger, and ring down for three massive black hole mergers of different total mass. Down here you see another classic LISA source. That is what is called an extreme mass ratio in-spiral. It's the in-spiral of a stellar mass black hole or neutron star in a black hole of mass about 10 to the 5, 10 to the 6 solar masses. And then one thing that was realized soon after the LIGO detections is that there's a third class of black hole binaries that we can see with LISA, and those are binaries that are massive enough, like GW150914, start their in-spiral in the LISA band, and depending on how early they start, they could eventually merge in the LIGO band, and these are called multi-band binaries. So I'll start by briefly discussing these multi-band binaries. This is the plot from Alberto Cesana's paper where he first discussed this kind of source. And the key idea is that you should keep in mind that by the time LISA flies, we will not have LIGO class detectors, but we will have detectors that are much more sensitive than that. So the typical redshift out to which we can see black holes of different masses is the one shown over here, where the low mass black holes correspond to, so what you see here are the horizons out to which you can see binary black holes with a given redshift that is indicated in numbers and colors. So what you see is that a detector like the Einstein telescope could see black holes of mass 10 to the 2, 10 to the 3 solar masses all the way out to redshift of order 20 or so, and LISA would see these guys out to very large redshifts. So if you ask what kind of science can you do when you put these two classes of detectors together, typically, if you take a source like GW150914, it will see a third-generation detector like Voyager or Cosmic Explorer will see that source with an extremely high signal-to-noise ratio of order 700 or 2,000. This means that we can measure the parameters of the source from ground-based detectors alone to an accuracy that is about 1 over the signal-to-noise ratio, so 1 part in hundreds or thousands. However, LISA is still useful for these multi-band sources because it can break degeneracies. We have white paper submitted to Astro 2020 with Kurt Cutler and my student and other people, where we showed that you could use LISA to, for example, measure the chirp mass of intermediate mass black holes, and then measure their total mass when they merge in the ground-based detectors later on. Or you could use LISA to measure the individual components of the two members of the binary as they in-spiral together, and then with LIGO you could measure the effective spin parameter that Michael was discussing this morning. Another thing that you can do is ask not what LISA can do for LIGO, but ask what LIGO can do for LISA. So, for example, LISA could, if you have several 3G detections, you can use those 3G detections to go back to your LISA data and say, well, since I can measure the time of coalescence using LISA with an accuracy of order seconds, if there is an event that I see in a 3G detector, I can use it to lower the signal-to-noise ratio threshold that I need for detection in LISA. And if you do that, you can use these coincident detections to increase the number of multi-band events that would be seen in LISA by a factor of about 8. We showed this again with my student Case Wong in a PRL. And yet another thing that you can ask is, can LISA help you to understand properties of subpopulations of binaries that will end up merging in the ground-based detector band? One obvious idea is eccentricity. Even if you have a binary that is circular in the LIGO band, it may very well be highly eccentric in the LISA band, and you could use LISA to measure eccentricity as long as the eccentricity is larger than about 0.01. And another thing that you can ask is which subpopulation of binaries, say within the field formation scenario, would be detectable by LISA, and this is something that we investigated in this paper. I will not go into details of that. Second thing that I want to discuss are massive black hole binaries. We had a very good talk by Priya this morning on the properties of massive black hole binaries, their rates, and so on, so I will not say much about this. But one take-home message from Priya's talk was that the rates for massive black hole binaries are extremely uncertain because we don't know whether the initial seeds were light or heavy, and we don't know how often these binaries merge and so on. A few years ago with my postdoc Antoine Klein, we estimated rates for different classes of LISA detectors, and you should focus on whatever is in this light green box. Those are rates under the assumption that you have either light seeds, so your binary black holes are of population 3 origin, or heavy seeds, Q3. And D and no D means that we either include or do not include a delay between galaxy mergers and binary black hole mergers. And what you can see here is that the typical rates that you get are anywhere between a few tens and up to several hundreds during the duration of a 5-year LISA mission. Now, what can you use these binary black hole mergers for? First of all, you can do measurements that are extremely accurate by astronomical standards. You can, for example, measure the masses within an accuracy of about 1% for a number of binaries that is indicated in this table. I don't expect you to read all the numbers in the table. I just want to point you to this paper as a place where you would see the kind of abilities that LISA has. You could measure the primary and the secondary spin within about 1% or 10%. You could measure the orientation of the two spins within about 10 degrees, and the remnant spin within about 10%. But the most interesting thing is probably the fact that unlike stellar mass binaries of the kind that we're observing with LIGO, we do expect to have substantial amounts of gas around supermassive black hole binaries. And so you could imagine using LISA binary black hole mergers as standard sirens, because if you can locate them in the sky accurately enough, you can associate a redshift to those mergers, and with that you can use them as standard sirens out in the very early universe. So what you see down here is how many binaries can you localize within 10 square degrees and determine their distance within 10% at redshift less than 5, where you can hope to go after electromagnetic counterparts. Finally, one of the promises of LISA is that you can see very low mass black holes of the kinds that were discussed in the talk just before mine, out to very large redshifts. But if you want to use LISA for that purpose, you should not just be able to observe those black holes, you should also be able to determine that they were actually at high redshift. Otherwise, you wouldn't be able to claim that you're observing an early merger. And so you want the distance determination to be accurate enough that you can make that claim. And here are some numbers for how often you can do that. Now, when we observe these binaries, we can set very tight constraints on the formation scenarios that Priya was talking about. Because, for example, if what you see here are plots, I won't spend too much time on this plot, but basically the thin lines are models of binary black hole mergers, and the thick lines are how many of those binaries would be seen by LISA. And you can see that in light seed formation scenarios, there are several light black hole binaries. This is similar to the plot that Angelo Ricarte and Priya made, that LISA would see if the early seeds were light, but LISA wouldn't see them if the early seeds were heavy. So you can easily do model selection and determine whether the initial seeds were heavy or not. And if you measure the spins, which you can do as I have shown a minute ago, you can tell whether these black holes grew mostly by mergers or by accretion. And the reason is that if black holes grow mostly by merger, when you have two black holes that come together, they will form a final black hole of spin about 0.7. So overall, your statistical distribution of spins will tend to cluster at 0.7 as time goes by. While if black holes grow by accretion, if accretion is mostly coherent, it will tend to spin up the black hole, so the spins will cluster around one. And if accretion is mostly chaotic, it will tend to spin the black holes down. So by doing statistical measurements of the spin, you can determine how these black holes grew. Finally, I want to mention extreme mass ratio binaries. Once again, here there are huge uncertainties, and we had a study here led by Stas Babak, where we considered a bunch of different uncertainties in computing rates. One of the things that was realized after the first LIGO detections is that perhaps the small black hole that falls into the larger black hole in an extreme mass ratio spiral could be more massive than we anticipated. And that will change the detection horizon. So what you see here is the detection horizon for extreme mass ratio spirals. Focus on the green lines that correspond to the most accurate model that we had based on Tsiolkovsky waveforms. And you can see that if you take a 10 solar mass black hole falling into a massive black hole of the mass shown on the x-axis, the typical redshift out to which you could see these things is of order 3. But if your small object falling into the larger black hole has a mass of order 30, then you could see it maybe out to redshift 5 or 6. And of course, this has a huge impact on the rates. Other things that have an impact on the rates are the massive black hole mass function that we don't know very well at low masses, whether or not there is cusp erosion after massive black hole mergers, because if you erode cusps, then you will not have as many mergers at the center of galaxies. The n-sigma relation is very uncertain. And also another thing that we don't know is the ratio of plunges to mergers, because if you have too many plunges, too many objects falling directly into massive black holes, they will not produce detectable gravitational wave signals. So there's an interplay between how many objects fall into a central black hole and how many produce signals that are detectable. When you put all of these things together, you get huge uncertainties in the rates, and they can go anywhere, as you can see here, from a few per year to 10 to the 4 per year. What kind of science can you do with these things? Well, first of all, you can measure the mass of the central black hole very well, so you could resolve the mass function of massive black holes at low black hole masses, where it's currently very uncertain. Another thing that you can do very accurately is improve on the kind of measurements that experiments like gravity are doing right now, because these objects are going to be highly relativistic and very close to a central black hole, so you can measure the higher multiple moments of the gravitational field distribution. And this plot shows you how accurately you could measure variations from the Kerr quadrupole moment, depending on your assumptions again, and the typical numbers that you get are pretty amazing, of order 10 to the minus 4, 10 to the minus 3 perhaps. Okay. Now, as I promised, I will move more and more toward theoretical physics. And the next thing I'm going to discuss is whether you can tell, using LISA, that these objects are indeed the Kerr black holes that are predicted by general relativity. And the general idea here to do this is based on the following picture. Suppose that you take a black hole that is non-spinning and you scatter some test field on that black hole. The scattering problem is described by a potential barrier that for a standard Schwarzschild black hole has a peak around 3m, the location of the light train, and decays to 0 at infinity. So if you require that you have purely ingoing waves at infinity, purely ingoing waves at the black hole horizon and purely outgoing waves at infinity, so that the black hole is spontaneously excited, if you like. I don't need to throw any waves at the black hole in order to excite it. You get an eigenvalue problem, and this eigenvalue problem has an infinite number of discrete solutions that are called the quasi-normal modes of the black hole. The key thing that you want to know is that all of those quasi-normal modes are determined only by the mass and the spin of the black hole. Now, suppose that the field perturbing the black hole has a mass. The same considerations apply with the one crucial difference, which is the fact that your potential now doesn't go to 0 at infinity, but it goes to a finite constant that is equal to the mass of the field squared. So now you can create quasi-bound states that may have a frequency that falls in the superradiant regime. If the frequency falls in the superradiant regime, then what happens is that you throw a wave into the black hole. The wave is partially reflected and partially transmitted. And If you are in the superradiant regime, the wave that is reflected can have an amplitude that is larger than the original amplitude. But now there is a boundary condition at infinity that is reflecting again, and so this process continues indefinitely and you create an instability. Basically, you keep extracting rotational energy and mass from the black hole until the black hole spins down to a lower mass and a lower spin, and you have transferred all of that energy to a boson cloud that has grown around your black hole. As I will discuss later, this has several potentially observable consequences. Now, the first thing that I want to point out is that LISA is a phenomenal instrument to detect quasi-normal modes and test whether these objects are indeed Kerr black holes. What you see here is a plot of the typical horizon out to which LISA could measure the fundamental 2, 1, 3, 3, 4, 4, and lower order LM quasi-normal modes. And basically, you can see these things out to enormous redshifts, and you are really limited at this stage by your ability to do data analysis for the lower order modes and by the confusion that will inevitably arise because you are seeing tens or hundreds of these things, and so you want to look at the brightest binary black hole mergers and then look for these lower order modes that may be swamped under the other signals that are louder than that. I will not say too much about this. What I will focus on instead now is superradiance and the possibility of detecting dark matter using binary black holes with LISA. Here the general idea is the following. Suppose that you consider a Klein-Gordon equation on a black hole background, and you take the non-relativistic limit of that Klein-Gordon equation that corresponds to a Schrödinger equation. So the fine structure constant in this case is basically the product of the mass of the black hole times the inverse Compton wavelength of your bosonic field. And this means that for a black hole of a solar mass, you need, for superradiance to be strong, a typical field that is of the order 10 to the minus 10 electron volt, because you want this fine structure constant to be of order unity. Now, because you have a problem that is completely identical to the hydrogen atom, what you get are states that have real part of the frequency that is hydrogenic with a typical frequency that is set by the mass of the scalar, and a Bohr radius that is given by the usual formula. But in addition to that, because your problem is not self-adjoint, you have an imaginary part of the modes that can be positive or negative depending on whether you are in the superradiance regime or not, and it scales with a very high power of alpha. Besides, if you go to higher order, what you can find are corrections to your hydrogenic spectrum that involve higher powers of alpha and a hyperfine splitting induced by the spin of the black hole. So at this point, you can have transitions between the different levels of your gravitational hydrogen atom that involve either Bohr transitions between states with different n, or hyperfine splitting transitions that correspond to transitions between states with the same n and different m. Okay? Now, what are the typical time scales for the superradiant instabilities that we discussed so far? Well, if you take a LIGO-like source, you find that a cloud around a black hole of the kind that is formed after a merger could form on a timescale of the order of months. And once formed, those clouds will radiate away very, very slowly on timescales that are typically of order 10 to the 4 for LIGO-like black holes, 10 to the 4 years. So the process is you have a spinning black hole. If there is a scalar field that has the right Compton wavelength, it can grow a cloud around a spinning black hole. The cloud will typically grow over a timescale of order months for LIGO or much longer for LISA. And then it will radiate over a much longer timescale gravitational waves. And this is basically a gravitational pulsar that emits monochromatically with a slight drift that is actually an updrift instead of a spin down. So this signal is something that you can go after. And what we did in this paper here, led by Richard Brito, was compute the amplitude of gravitational waves as a function of the mass of the bosonic field, And we found that there are certain ranges where these monochromatic signals would be detectable. But it's even better than that, because there are so many black holes in the universe that if any bosonic field in the right mass range exists, all of the black holes that are close to the mass that would be resonant will emit one of these monochromatic signals. So you will end up having a stochastic background that, if the mass of your bosonic field is optimal, should already have been detected by LIGO. And in fact, there are people in this room who have been working on doing data analysis for monochromatic signals of this kind, and the fact that you don't see them sets upper bounds on bosons of mass of about 10 to the minus 12, 10 to the minus 13 electron volts, and you could do the same for LISA in a very different mass range. Another way that you can go, so I promised you that there will be 4 different signatures. I'll be very fast. I know that I'm running over time. The second way that you can look for these signals is, if there is a superradiant instability, we should not be seeing very highly spinning black holes. But LISA, as I told you before, can measure the spins of black holes in binaries very accurately. So if LISA does not measure black holes of mass 10 to the 4, 10 to the 5, 10 to the 6 that are spinning very fast, it can rule out a very broad range of black hole masses. When you put these two things together, you find that LISA could either measure the bosonic fields of mass between 10 to the minus 18 and 10 to the minus 16, roughly, or it could rule out boson masses in the range between 10 to the minus 18 and 10 to the minus 13, because you don't see very large spins, according to the idea I just described. I want to describe 2 more things very quickly. The first is, consider those transitions between levels of the hydrogenic-like boson cloud. Whenever you have a binary system, the companion of your black hole plus cloud will exert a tidal force, a tidal field on the cloud that can cause transitions between the levels of the cloud. Those transitions can happen either when the frequency of the binary corresponds to the hyperfine splitting between levels with different m and same n, or when you have a counter-rotating orbit where the frequency is resonant with the Bohr transition frequency between states with different n's. Okay? So this is the situation. There are selection rules that I will not get into, but whenever this happens, you can deplete the cloud quite dramatically. And here, I show you an approximation down here and a more precise calculation done up here of how much you could deplete the cloud. The bottom line is that you could have an almost complete depletion of the boson cloud in very broad regions of the alpha versus mass ratio parameter space. If this happens, there will be a dramatic signature in the in-spiral, because you start with a black hole with a cloud that can be up to 10% of the mass of the black hole. You go through a resonance, you deplete the cloud by about all of the amount of mass that used to be in the cloud. So you reduce the mass of one of the binary components by about 10%, and of course your in-spiral will slow down dramatically every time this happens. So you can go after this with LISA and potentially measure boson masses. And this tends to happen much more often in LISA than in LIGO for reasons that I can explain if you want. Finally, the very last thing that I will mention, suppose that you have one of these bosons with a large cloud around it, and you consider an extreme mass ratio in spiral. Now your small black hole is not falling into the vacuum spacetime of the big black hole, but it's falling in the spacetime of the black hole with the cloud. And we know from theory exactly what the cloud looks like. We can predict all of the mass distribution in the cloud. So we can measure the mass of the boson through the gravitational waves emitted by the extreme mass ratio in spiral in several different ways, and verify the hypothesis that we're not actually looking at a naked black hole, but we're looking at a black hole that is surrounded by that specific cloud. And we have done a proof of principle that this can be done. Once again, I can go into the details if you're curious. And I'll stop here because I'm over time already. Thanks.
Okay, questions? Yeah, so just here.
So, very nice talk. So how long does the boson cloud take to assemble in the first place?
That was the time scale that I've shown you before. If you look at it scales with a very high power of alpha, So the typical time scale, you see it here, is the instability time scale. And for a black hole of 10 solar masses, the power is power of alpha to the 9. But superradiance is very effective when that alpha is of order 0.4. That's when you get the maximum. And a typical time scale for a LIGO-like binary is of order weeks, maybe months. The growth
That's
of the
the
cloud.
growth of the cloud, right?
That's the time
Before
it
you
takes to
start
assemble the
seeing-
cloud. Yeah,
Right.
that's what you were asking.
Then it can stick around, but
Yeah.
it can be very long-lived,
Yes.
right? Okay.
Yes.
And so the depletion can be quite slow.
Yes, so there's two ways that the depletion can happen. One is by what people call annihilations. So basically, if you think of it in terms of Feynman diagrams, what you have here is two bosons that annihilate and produce gravitons. And that's the dominant gravitational wave emission mechanism. It's the one that produces the pulsar-like signal. The level transitions, they tend to produce much weaker gravitational radiation, and, but they are still very effective if you have basically stimulated emission at the relevant frequency, which is what will happen in a binary.
So there'll be a fluctuating strain that you can, okay.
Yeah. You would see a spike, a very slight spike, that corresponds to the level transition, and then your signal from the binary should plateau at a lower level because you have radiated some of that mass into gravitational waves.
But this also has implications for final mass estimates, right, that you derive. Because if we are not seeing all the superradiance structure at the moment, we are not resolving it, then we could be off in the masses, right? Because
Yes, but
tiny amounts, yeah.
yes. Yeah.
Okay. Okay. One quick question. Yeah.
So you're talking about all these extremely low mass bosons, 10 to the minus 17 eV and all that. What kind of candidates do we actually have for particles with that kind of mass?
Yes, so that's a very good question. So typically, people consider these are not the kind of bosons that you would use in fuzzy dark matter scenarios, right? This mass range is higher than what you need if you're thinking about things like the paper by Lam Hui with Ostreicher and, okay. So the typical motivation for looking at these things are things like the string Axiverse scenario, where, you know, if you have compactification of higher dimensions, you will produce a spectrum of bosons that can be wherever you want. More in general, it's just interesting to go after dark matter in a mass range that has not been explored by other means. So.
Okay, if we could thank our speaker once again. I'll give you like a 5-minute warning. I can give you a 5-minute warning if you like.
Yeah.
Okay, good. Okay, so our final speaker in this session is Professor Dennis Lemkool from the University of Bonn. He specializes in history and philosophy of physics and the philosophy of science more generally. And today he's going to tell us about the history and philosophy of the event horizon.
Thank you. Okay. This isn't on yet. Is it on? Yeah, thank you. Thank you very much. It's an honor to be here today, especially given that it's only a few weeks ago that the Event Horizon Telescope showed us a black hole for the very first time and arguably showed us the shape of the event horizon. And as you all know, the very concept of the event horizon and of black holes is much younger than general relativity itself. It came into existence 50 years after Einstein found the field equations. And that whole process, how this came about, why it took so long, and how it took place, is something I want to understand a bit better. And the history, as so often, is multifaceted, and it has three important strands or three important dimensions that I want to speak about explicitly. The first is the topic of distinguishing between real versus apparent singularities. So what we would today speak of coordinate singularities versus actual singularities of the physical spacetime, and how that distinction evolved, how it came into being, and how people classified singularities or properties of solutions to the Einstein equations in different ways at different times. And I'm going to start out by speaking about another Einstein myth, namely that Einstein was essentially confused in his analysis of the Schwarzschild solution. I think it's a much more interesting story. And I'm going to then speak about how the analysis of the Schwarzschild solution, of the Schwarzschild metric, brought about a development that went far beyond understanding that particular solution and brought about the concept of black holes and event horizons in the 1960s, especially in the work of Roger Penrose and his contemporaries, and how, in a way, that is really the point where general relativity, as we understand and use it today, came into maturity. So I'm going to speak first about another Einstein myth, and that myth is you see it in the title of this slide, which is, I've seen a sentence like this said or written by many historians and philosophers of physics and by some physicists as well. So the claim is that the Schwarzschild metric was found in 1916, but it took more than 50 years until people understood that it actually represents a black hole. And so this sounds a bit as if Einstein and his contemporaries were basically confused or that they didn't get it. And I think the truth is much more interesting. I think, in fact, how they understood the Schwarzschild metric was embedded in an entirely different conceptual network of methods, concepts, and applications of general relativity that is very, very different from how the theory and the Schwarzschild metric in particular came to be used from the 1960s onwards. And I'm going to speak about this in detail. And I think one reason why it's interesting to clear this up is because, well, first, it gives us a more subtle understanding of how Einstein and his contemporaries thought. And it also drives home the fact of how big the changes were that happened in the 1960s when the concept of event horizons, black holes, and trapped surfaces were developed, and how they completely revolutionized, again, general relativity. So here's the Schwarzschild metric in Schwarzschild coordinates. As you know, there are two singularities in these coordinates, one at r equals 0, and the second at r equals 2m. And the latter, so the r equals 2m singularity, was soon called the Schwarzschild singularity, and the former, the r equals 0 singularity, seemed familiar. So this was not something new, the r equals 0 singularity. This was not something that people worried about at the time, because they had encountered this type of singularity again and again. So in the spherically symmetric solution to the Newton-Poisson equation, you have an r equals 0 singularity. And in the spherically symmetric solution of the Coulomb equation, you also have an r equals 0 singularity. And people didn't worry about this, primarily because they thought of this as an artifact of the description and an artifact to be expected, because at the place of the singularity was where you expected matter, and you had not really modeled matter. And so it was not surprising that something strange happened at this spot where you hadn't really included all the physics. So what people really worried about was this new type of singularity, the r equals 2m singularity. Again, so the r equals 0 singularity wasn't something they really worried about. And Einstein in particular didn't worry about it because he saw it as a placeholder for a theory of matter not yet delivered. So this is essentially how he went about deriving the perihelion of Mercury in 1915. So that was before Schwarzschild found the exact solution. So Einstein was looking, took the linearized vacuum field equations and looked for a spherically symmetric, static, and asymptotically flat solution to describe the exterior gravitational field of the sun. And so this is all he really needed in order to describe or to derive the path of Mercury, right? He needed only the exterior gravitational field. He didn't need to know anything about the actual structure of the sun. He didn't even need to include the sun as part of the model. It was perfectly fine to take a vacuum solution and just look at the regime outside of where the sun started. And the fact that this solution, both for the linearized equations and then for the Schwarzschild solution that Schwarzschild found a year later, and that is the exact counterpart which Einstein's solution approximates, that these solutions had a singularity at equals 0, that was fine. This singularity they interpreted as a placeholder for the theory of matter not yet delivered. And in fact, Schwarzschild, in his second paper of 1916, quickly delivered the interior Schwarzschild solution and got rid of the singularity from the vacuum solution. And so what people really worried about was not I equals 0, but the I equals 2m singularity. And in fact, it became somewhat notorious. So despite the fact that the I equals 2m singularities for all known stars, and that's something that Schwarzschild and Einstein already commented on in correspondence, would be inside the part of this inside the star, so it wouldn't really be observable outside of the star. Other people especially worried and wondered what would happen if we were to get closer and closer to that singularity. And there was a real industry of people giving names to the I equals 2m singularity. So here's a quote by Eddington from 1920, who said, "There's a magic circle which no measurement can bring us inside. It is not unnatural that we should picture something obstructing our closer approach and say that a particle of matter is filling up the interior." So the idea was, the closer you get, if you were able to get closer and closer to the I equals 2m singularity, given that the components of the metric become infinite there would be no way for you to get through. It would be a kind of a magic circle or a barrier which could not be passed. And other names for the I equals 2m singularity that people use in the 1920s are the discontinuity, Schwarzschild name, the barrier by Kotler, the sphere, Weil, the gravitational radius also by Weil, the hole in the world by Reichenbecher, the singular frontier, the catastrophic frontier, and the limit circle. This was all Briorin, who was on a run. And finally, the death by Nordmann. And looking back, even at the time, actually, when people were thinking of the Schwarzschild singularity as a barrier that could not be passed, people must have noted, although I didn't see it noted anywhere in writing, how much it looked like destiny that the person who discovered the Schwarzschild solution and also the Schwarzschild singularity was Karl Schwarzschild, whose name in German literally means black shield. Just happened. And so people got more and more uncomfortable about the Schwarzschild singularity, the I equals 2m singularity, during the 1920s. And in particular, the question was, can we really get by saying it's a mathematical artifact, something that would never appear in nature? And especially during a conference at the Collège de France in April 1922, Einstein was giving a talk about general relativity, and he was presented by what he quickly came to call, half in jest, half in seriousness, the Hadamard catastrophe, because Jacques Hadamard raised his hand and asked, couldn't it be that a star or another heavenly body would acquire so much mass and would collapse under the strength of the gravitational attraction of its parts, so that the Schwarzschild singularity would end up outside in the vacuum regime, outside of the star? And Einstein called this the Hadamard catastrophe, because if it were to happen, he felt that would strongly speak against general relativity as such. And he came back during the conference, so he went to his hotel on one day after Hadamard had brought forward the point, and came back the next day with an argument of why this could never happen in nature. I can come back to what his argument was in the question period if you want. But what I want to focus on here now is why it would have been a catastrophe for him in the first place. Why would it have been a catastrophe if the I equals 2m singularity ended up being outside the astronomical body? And I think the reason is Einstein's interpretation of general relativity and what it was supposed to do as it developed, or at least was explicated by him in the 1920s. So I believe that Einstein regarded general relativity as what I would call a hybrid theory, fundamentally correct with regard to space-time regions containing only gravitational fields, and only phenomenologically correct with regard to space-time regions in which matter is present. So the energy momentum tensor NGR and any solution to the full Einstein equations with a material source, the energy momentum tensor was only a placeholder for a not yet found adequate quantum theory of matter. So the energy momentum tensor and anything involving him was not really to be trusted. And thus, Einstein was fine with introducing singularities to stand in for matter, to see singularities as placeholders for a theory of matter not yet delivered, because this just meant replacing one placeholder, the energy momentum tensor, for another placeholder, a singularity, like the r=0 singularity in the Schwarzschild metric. But the point was, for him, these types of singularities were fine, singularities that could be interpreted as being placeholders for matter. But in space-time regions free of any matter, no singularities were to be allowed. And if the Hadamard catastrophe were actually to take place, that would exactly be such a singularity that was outside of matter in the vacuum region where general relativity was supposed to be fundamentally correct, rather than in the region where it's only phenomenologically correct. So that's why this would have been a catastrophe for Einstein, and why he was happy that he could convince himself that this could never happen. Now, during the 1920s, 1930s, and all the way up to the 1960s, a new understanding of the Schwarzschild metric came about, and it brought with it a transition from speaking about r=m as the Schwarzschild singularity to the eventual formation of what we today call the event horizon. So these two concepts, singularities on the one hand, event horizons on the other hand, were not at all distinguished until at least the 1950s. And they were only really solidified and completely clarified in the 1960s, primarily in the work by Roger Penrose, drawing on work by Rindler. The starting point, though, is the search for other coordinate systems. So already in the 1920s, Eddington, then Lemaitre in the 1930s, Robertson in the late 1930s, and Finkelstein in the late 1950s all found coordinate systems, arguably, by the way, also Painlevé and Goldstrand in the early 1920s, all found coordinate systems which got rid of r=m as a singularity. So they found coordinate systems that were entirely regular all the way across what corresponds to r=m in Schwarzschild coordinates. And so they, all of them saw that there was hence a way of getting through the barrier by using different coordinate systems. And it's interesting to look at what each of them, what conclusions they drew from them. None of them really completely went there and said, hence there is no singularity there whatsoever. Eddington even said, well, maybe part of the singularity that is there is due to the coordinate system, but there seems to be something else. So none of them really said there's nothing there at r=m, and the singularity in the Schwarzschild coordinates is only an artifact. And of course, to some extent, they were right. There is something more there. It's not just a coordinate singularity. And that part of the story would really play out in the 1950s and 60s. And one element, apart from finding these new coordinate systems, was that the state of the game and the stakes really changed in the 50s. Up until then, the whole discussion was more or less a theoretical discussion and a purely interpretational discussion of a vacuum solution to the Einstein equations, which had so far only been used for the r larger than 2m regime to represent the exterior gravitational field of stars. But now in the 1950s and 60s, the Schwarzschild solution was recruited to play a different role, namely from not only representing the exterior gravitational field of stars, but to also possibly represent the end state of collapsing stars. So there was a long discussion about whether a collapsing star would end up in a new equilibrium state that would basically keep it from collapsing further, or whether it would collapse all the way through I equals 2m, and which would lead to continuous collapse. So now in this new context, there was suddenly reason to worry about the r equals 0 singularity for the first time. Because, well, if a star would collapse and get smaller and smaller, and this would bring about a singularity, then it looked as if that singularity could actually appear in nature. And the placeholder interpretation was, so to speak, fading away, and people started to worry about whether singularities could appear as part of a physical collapse. And then there was a large discussion about, well, but if this happened, isn't this clearly due to the high symmetry of the Schwarzschild solution and an artifact of these symmetries? And as soon as you wouldn't have complete spherical symmetry, there wouldn't be any I equals 0 singularity. So that was a big discussion in the 50s and 60s. And also the I equals 2m singularity reared its head again, and it looked as if it was not just a singularity. And that is part of the final part of the story, namely when Penrose, especially in the 1960s, used the understanding of especially the Eddington-Finkelstein coordinate system to trigger a new development that also brought about a shift in general relativity from being entirely determined to use only local concepts to also global concepts and questions and methods pertaining to space-time geometry. So the path for Penrose was, well, first it's important to note that understanding that I equals 2m is not a real singularity is not the same as understanding that it is an event horizon, right? Because after all, there are many coordinate singularities that are not event horizons. So it's two separate steps, understanding that I equals 2m is not a real singularity and understanding that it is something else. And for Penrose, the formation of that concept, of the modern concept of the event horizon, was strongly inspired on the one hand by Finkelstein telling him about this coordinate system that could be interpreted as representing an infalling observer who would just go through I equals 2m and feel nothing special. And on the other hand, by Wolfgang Rindler, who had defined different horizon notions in the context of cosmology. And Penrose took the two of them together and brought about a modern concept of event horizons. And this happened, this is of course a quick version of the story, but this happened essentially in two ways. So he contrasted in a review paper in '69, and I'm coming back to the breakthrough paper of '65 in a moment, but in '69 he contrasted the classical collapse picture with what he called the generic collapse picture. The classical collapse picture, as he called it, was only really 5 to 6 years old. And it involved comparing what happens at I equals 2m in the traditional Schwarzschild coordinates and comparing what happens in the Eddington-Finkelstein coordinates. So in the Schwarzschild coordinates, and this was something that had been stressed for quite a while, it looks as if the light cones of an infalling observer would just, because he could never cross, he would get closer and closer to the barrier, and he would be stretched, and it looked as if he would be ripped apart. That was an old picture of what happens at I equals 2m. I guess that's why Nordmann called it the death. And on the other hand, if you look at the same metric in Eddington-Finkelstein coordinates, there is no singularity at what corresponds to I equals 2m, and instead you trigger through. Actually, I have it here a bit bigger. Now, what is striking is that this comparison, right, this was what Penrose still presented as the classical collapse picture, that there is this perspective, and then there is this possibly much more telling perspective, where the observer, and arguably hence also the matter in a collapsing star, would just go through I equals 2m and would just keep collapsing. And for the observer that is infalling, that is, so to speak, sitting on the surface and collapsing with the star, nothing special would happen at the counterpart of R equals 2m. And Penrose stated, still in the context of presenting the classical collapse picture that he was about to try to overcome, Although the hypersurface r equals 2m has in the past itself been frequently referred to as the Schwarzschild singularity, this is really a misleading terminology, since r equals 2m is a singularity merely of the t-coordinate used in Schwarzschild coordinates and not of the spacetime geometry. More appropriate is the term event horizon, since r equals 2m represents the absolute boundary of the set of all events which can be observed in principle by an external inertial observer. Now, this is already a strong clarification, right, of what is happening, a new understanding or solidification of a new understanding of collapse as it had come about in the previous 5 to 6 years. But it still does not clearly say what is special about what we today call the event horizon, r equals 2m, from the viewpoint of the infalling observer. Although it's already hinted at, if you look at the light cones at r equals 2m, where you can already see that the entire future light cone is directed towards the singularity. So you already see what would become an essential part of the concept of an event horizon, that it's a spot where, as a point of no return. And this observation Penrose used in order to motivate and bring about what he then called the generic general relativistic collapse picture, so named in '69. And so he wrote, so here's another perspective, in contrast to the one just described. After the matter has contracted within r equals 2m, a space-like sphere can be found in the empty regions surrounding matter. The sphere is an example of a trapped surface, defined generally as a closed space-like two-surface with the property that the two systems of null geodesics which meet at the surface orthogonally converge locally in future directions of the surface. And so this idea, this concept of a trapped surface, it's today hard to fully appreciate the ingenuity that introducing that concept took at the time, because it's the kind of concept that once it's been supplied to you, it's very difficult to take a step back and to imagine how things were before, because it seems so entirely appropriate to the situation, so entirely appropriate to describe what happens in collapse, that you see it here. This is also from the Penrose 65 paper. So here you have the r equals 2m singularity, or the event horizon, as he had already called it, and it's inside the trapped surface that would get smaller and smaller. And so it's immediately clear how helpful the concept is to describe what is happening in collapse. But one has to see that a coordinate system like the Eddington-Finkelstein coordinate system was necessary to inspire this idea. But once you have it, you see that the whole concept is entirely independent of any allusion to a particular coordinate system. It doesn't need to refer to any symmetries of a given space-time, and it is clearly a global concept, whereas before the entire tradition in general relativity was to focus on local concept. Right? In a way, that was the big mission of Einstein and Weil starting in the late 1910s, get away from Newtonian gravity with long distance concepts and focus on the truly infinitesimal geometry, be very, very distrustful of anything that looked like global structures. Partly this is also related to what Einstein called Mach's principle. Everything has to be local rather than global. And now with the concept of a trapped surface in hand, Penrose could prove the very first singularity theorem, which showed that the trapped surface is that which brings about singularities in a way that cannot be circumvented. So basically the conclusion of the first singularity theorem is that the existence of a trapped surface implies, irrespective of symmetry, that singularities necessarily develop. And he went on to then discuss the question, so now that you have the concept of the trapped surface, what becomes of the event horizon concept? And he went on in '69 to say, what qualitative peculiarity of the region r equals 2m after the star has collapsed through is present? can such peculiarities be related to the fact that everything appears to be forced inwards in the direction of the center? It should be stressed, again, that apart from r equals 0, the space-time at any individual point inside r equals 2m is perfectly regular. So the peculiarities of the region between r equals 0 and r equals 2m must be of a partially global nature. And note how much this goes beyond just realizing that the Schwarzschild singularity is not a real singularity. It really shows that r equals 2m is an entirely different type of animal. It's not a singularity, it's an event horizon. And these two notions have really only properly come apart at this stage in the development of general relativity. And this is just not something I can speak about in detail, but it's the beginning of an entire series of global concepts and methods that Penrose introduced in the 1960s, trapped surfaces and event horizons, as I just said, which brought about, with the way that the singularity theorems worked, a shift from speaking about singularities, local singularities like curvature singularities or singularities in the metric field, to the notion of singular space-time via geodesic incompleteness, also a global notion, discussions of asymptotic properties for space-times, causal structure, all of this happened in these years. And I think it is fair to say that it really brought about a shift that is really quite revolutionary compared to how GR looked in the 1910s and in the 1920s, where the focus was on local concepts of space-time geometry, and now, for the first time, global concepts and methods and applications entered the scene. Okay, so to sum up, well, it's not really summing up, it's just stating that I think one thing that the story of the Schwarzschild metric shows, or it's an instance of what Griffith and Podolsky said in their book on exact solutions to the Einstein equations. It appears that it is much easier to find a new solution of Einstein's equations than it is to understand it. So it's definitely true that it only took Schwarzschild a very short time to find the Schwarzschild metric, and then it took years and years, decades, to really understand the Schwarzschild metric in the way we understand it today. But I do think that this is not a matter of back then they were confused and they should have known better, and now we know better. I think any such instinct is really brought about by projecting backwards, having the notion of a trapped surface and of an event horizon in the modern sense in our hand, and projecting backwards. They had an entirely reasonable belief system and interpretation of general relativity. It's just that it didn't carry on. There was something better that was just not yet at the horizon. And so I'll finish with a quote by Hund, who said, well, how difficult were these advances? If we now acquaint ourselves with some of the detours, errors, and psychological blocks, it is not to console ourselves with the thought that even the great physicists do not always move in a straight line, but rather to grasp in some measure how difficult it really was. Thank you.
Okay, questions? So, Ramesh.
So, there was this famous paper by Oppenheimer and Snyder, late 30s, where they looked at the collapse of a dust cloud, spherical dust cloud, all the way down to a singularity, happily going through 2M, and they pretty much laid out the whole space-time solution as a function of time. Didn't it have any impact on all these people who are still struggling with concepts?
It did. I mean, first of all, the reason that, thank you, I wish I could have spoken about this too. And I mean, first of all, there was a bit of a delayed impact because of the beginning of the war, the Second World War. Similarly to Dan's story, in both cases there was a strong influence. So it wasn't really cited and taken up for a long time. But some people did. So, I mean, we know that definitely Robertson, Tolman, and Einstein knew about some of these results. And Einstein even wrote a paper arguing that collapse in that way wouldn't happen. And so this is something, this is an episode that I still work on together with a colleague from Amsterdam, Jeroen van Dongen. And it's an interesting story, and it's also there. It's easy to look at it and think, well, why didn't they get it? It's so clear. But even if you then go to the 1950s and 60s, when people were discussing explicitly about gravitational collapse, and Oppenheimer and Snyder had been rediscovered, and you have Wheeler and Coma and the whole gang discussing what does gravitational collapse really lead to. And people were not convinced that this is really the right picture. So there was one of the Texas conferences. Wheeler discussed the question of, well, gravitational collapse, what would happen, what could be the final state of equilibrium, and so on, right? And he was really trying very hard to find an argument that there would be a stable equilibrium state. And Oppenheimer was in the audience and raised his hand and said, well, but you're really forcing yourself here. I mean, wouldn't it be just easier to admit that what happens is a continuous collapse all the way down to a singularity? And Wheeler said, no, I don't think this is what's happening. And so even when people were aware of it, and the people of the new generation, it was still not getting all the way through.
Could they point to something that was wrong in Oppenheimer's Snyder? They say it cannot go the way they described because of such and such.
Well, one thing that many people believed, and I've alluded to that already, was they thought it was an artifact of the spherical symmetry that Oppenheimer and Snyder did assume, right? They assumed it, or it could have been an artifact of the dust cloud that they assumed, very highly idealized matter model. So there were all kinds of parts of Oppenheimer and Snyder where you said, oh, well, that is an assumption that is questionable, and then hence the conclusion is questionable. So that's basically what happened. Yeah.
This confusion.
Yeah.
To put it somewhat pejoratively, lived on for a while.
Yeah.
The question is about curvature. On my, especially compared to yours, primitive understanding of the history is that people didn't really start getting straight on the role of Riemann tensor in the physics of gravity until the 50s.
Mm-hmm.
They didn't even fully put together the connection between Riemann and GeoDesic deviation.
Yeah, that was Pirani, yeah, and Sinch, yeah.
And so I'm curious. You never mentioned curvature. So it seems clear that before the 50s, they couldn't have used curvature as a proxy for what counts as a singularity, what doesn't, or at least couldn't was too strong, but maybe not.
Yeah.
But by the 60s, they could have. But it seems as though they almost instantly moved away from curvature, blow up, and it's jumped straight into geodesic incompleteness. Do you have any sense of why that might happen?
Well, I'll answer in two parts. First, about the early phase, right? You're right, of course, that the whole, the focus on the curvature tensor, especially via geodesic deviation, comes also in the 40s and 50s with Sinch and Pirani. But the Kretschmann scalar as a curvature scalar, well, was defined by Kretschmann in the 1910s. And there are definitely places where people discuss curvature, what we would today call curvature singularities. The Riemann, the Ricci scalar can become singular, just like the metric can become singular. I think it's just that they didn't really see a difference. Well, the metric can become singular, the curvature scalar can become singular. It's the same type of thing, and they weren't really seeing a difference there early on. And I don't think that they really jumped straight to geodesic incompleteness. Even in Penrose's papers, when he the theorem that he proves in the 65 paper is very clearly saying, well, trapped surfaces bring about singularities, and singularities is defined via geodesic incompleteness. But then in the 69 paper, he has a long discussion of what this really, how this should be interpreted and what this really means. And he's very, very careful to say, this does not tell us that there is a singularity or a curvature singularity at r equals 0 in the Schwarzschild case. It only tells us that there is some singularity somewhere. It doesn't tell us whether the singularity is physical or where it's located. So this, even after you have this notion of geodesic incompleteness, there's still the thought that a real singularity is, or physical singularity is one something like a curvature singularity. And the question is being debated how the singular spacetimes criterion relates to the physical singularity criterion that is defined via curvature. And so this happens, I think, in step, in a way, and goes on into the 60s. So it's not that in 65 or 69 everybody said, okay, geodesic incompleteness, that's what it is to be singular or a singularity. And it's a much more complex story, I think.
Okay, so sorry, we should probably move on. So on that note, perhaps we could thank Dennis once again.
Thank you.
So now we'll have a coffee break and we'll be back at 4 p.m.
right. So thank you everyone to the last session of the day. So our first speaker is Professor Geoffrey Compère from University of Brussels, and he will tell us about signature of high spin in gravitational waveforms.
Thank you. It's my pleasure to be here. Thank the organizer for the opportunity to speak here today. I would like to review some work done on the modelization of gravitational waveforms for binaries, where one component is a very high spin. And there are plenty of very nice properties that arise and signatures of gravitational waveform, and I would like to explain that here. But first, since this is an interdisciplinary center, I would like to start with the motivation from astrophysics. 2 years ago, Laura Brenneman was here presenting results, and here is a table from her paper showing that out of this X-ray survey, active galactic nuclei are candidate high-spin supermassive black holes. Out of 22 AGNs that were observed in X-rays with this study, 7 had a spin which was more than around 0.98 compared to the maximal high spin possible. So this is very encouraging that these high spin black holes might exist. And how high can the spin be? Well, according to the cosmic censorship conjecture, which theorists like me strongly believe in, the mass rate, the A over m has to be less than 100%. There is a standard bound that everybody in astrophysics is using, which is the tone bound, which was derived from thin disks accretion. So this ratio cannot get bigger than this number in this thin disk accretion model. Though it was shown that if you have magnetic fields and if you have thin disks that are supported by magnetic fields, their innermost edge, instead of being at the ISCO and the innermost stable orbits, can lean towards the IPCO, the innermost bound orbit. And then the balance of spin changes a bit, and it depends how close you can go to the IPCO. But in the theoretical limit where you go all the way to the IPCO, you can go all the way to around 100%. So the highest number I saw in the literature is this number, which was a mandatory dynamics simulation, where they reach 0.9994, which is higher than the tone bound in some slim disk model. But in theory, I don't know, maybe there was some other model of disks that we haven't seen before and that could reach a higher bound. So I'm just a bit agnostic about this. And they also work on absorption of objects, but they tend to lower the spin, even though if you fine-tune your parameters, you can always try to spin it up, but on average, they don't do that. There are also encouraging features arising from population models. So I take this study from Bertie and Voluntary, that if you have very high masses, the anisotropic accretion tends to spin up the supermassive black holes all the way to the maximal spin allowed by the local accretion physics, which is typically the tone bound, or some other bound if there is some other accretion possible. So for me, this is a possibility for high-spin supermassive black holes. Now, another motivation is to look at intermediate mass black holes. So we heard about it already today. There is a partial evidence from X-ray and optical astronomy, even though we haven't seen them in gravitational waves. And the IMRAC is an intermediate mass ratio coalescence. And this is called coalescence and not in spiral because the merger and ring down contribute to the gravitational wave signal because the mass ratio is not that high. The mass ratio if you have so you have two types of them. I forgot to say. So of course, either you have stellar mass falling into an intermediate mass black hole, or you have an intermediate mass black hole falling into a supermassive black hole, and that one is observable at LISA. And that's the one that I'm mostly interested in because of this motivation for high spin for the supermassive black hole. And I'm interested in this system because the merge and ring down have contribute to the signal. So it turns out there's not that much work that has been done on modeling all the process. The for extreme mass ratio, it's mostly done in spiral, but here we also need the final transition to collapse and the collapse phase. So the way to model this, numerical GR and post-Newtonian methods are not, cannot be used. So it's black hole perturbation theory, which has zeroth order, is finding a geodesic in Kerr black hole. But then you need to include corrections typically to have faithful, accurate waveforms, including cell force, spin coupling, some fine size effects. And I will use this seminal work that was done here, that in the high spin regime, there is a method that can be used to derive this using some match expansion methods with some simplification due to conformal symmetry. So I will basically elaborate on this. So let me start the proper talk. So I will just assume now that we have an extremely high spin. So higher at this bound. And this is interesting in its own right as mathematics if you are not sure about the astrophysical motivation. It's very useful, I think, for a benchmark for numerical simulations and benchmark for effective one-body methods on its own right. So the first feature is that if you have this extremely high spin, it was observed already in the 70s that you have new regions that open up, the near region around the ISCO and a very near region around the innermost bound orbit. And these two regions have a name, then called neck and near neck, near horizon extreme Kerr, while the far region just goes to extreme Kerr geometry. And the feature, the fact that you have these regions means that since the ISCO is in the near horizon region, this adiabatically evolved in spiral is also in that region. And this region is exactly correlating with the black hole. So it means that the time scale typical of for the gravitational wave oscillation is fixed to be the one of the extremal Kerr angular velocity. So this locked time scale is the first feature of these waveforms. It's a very simple observation. The second observation is that since this ISCO is this near horizon region, you can check that the amplitude is suppressed because it's redshifted. And the suppression scales with near extremality like a power 1/3. So that's also a very simple thing, but it's not that suppressed. I mean, lambda can be 10⁻3, and then this factor is not that bad. So for example, if you do an estimate for LISA, and you take around 10 to the 5 solar masses for the big black hole, and signal to noise ratio of 15, you can observe this signal for 1 gigaparsec. So it's not that bad. Now to describe a bit more the physics of this near horizon, of this signal, I need more features. One of them is this bifurcation of quasi-normal modes that happens for very high spin black holes. So the spectrum bifurcates, and has been shown by these people, into a zero-damped quasi-normal modes and the non-damped quasi-normal modes. The damped quasi-normal modes are sourced in the near region, while the damped modes are sourced outside in the far region. And if you look at these quasi-normal modes, they have all these zero-damped modes. They have all the same real parts, and they have equally spaced imaginary parts. So that leads to what is called a polynomial ringing. So normally, the ringing of black holes is exponential decay due to every individual quasi-normal mode. But here, since you have a sum, so basically in your waveform, you will have an exponential of I omega t. You replace omega by this. The I cancel the I, and then you have this exponential with equally spaced n. And so if you resum it and you look at intermediate period where t is small, you find that some polynomial type thing, like 1/t. But in fact, this is, of course, you have to look into the details of what is the green function and what is exactly, what kind of function do you have. And you need to know how much you are going to source each of these modes individually to know how you are going to have, if you are going to see this phenomena. So this is what we did. We computed using the Tukowski perturbation method, and I will explain a bit later how we could do this, but this is what you observe. This is the result. So it happens. You have this transient polynomial ringing, and it turns out to be between 1 over square root of the retarded time and 1 over the retarded time. And well, you have several trajectories because it depends on the impact parameters. I'm not going to explain the details, but there is an analytic formula for the exact gravitational waveform depending on the impact parameter to know how all these quasi-normal modes are excited. And then you sum them all and you find this behavior. And then you have the traditional exponential decay after a typical time, which is lambda minus 1. So you have more and more of this polynomial ring down with the closer to the high spin. Another feature is the higher multiples. So we all know the Einstein formula, the quadruple sources gravitational wave, and this is true in the post-Newtonian regime. But now here we are in the highly relativistic regime, in the strong field regime, and all the modes are becoming important. So if you and the way the higher modes become important depends on how you look at your system. So if you have this merger occurring and you look at it face on, with respect to the plane of rotation of your system, the amplitude, only the quadruple contributes. And you have this polynomial ringing, and then the standard exponential ringing. But if you look at it on the plane, so edge on, then the amplitude will oscillate strongly, which will depend on actually on all these higher modes. So the contribution of the higher multiple is a typicality of this strongly deep GR regime. So in particular, it allows sky localization of the source, which is very interesting because depending on how you look, the signal will look very different. So here you will have the pitch is fixed at the locked oscillation timescale, so it will be but here will be so it's the amplitude that changes, but the pitch remains the same because it's fixed. This is the feature number 1 that I showed you, right? The pitch remains the same. The oscillation is the same. It is really the amplitude that oscillates here. So now I turn more to the mathematical features because there are a lot of things to say, and I won't have time to tell you a lot. But one feature is that there is conformal symmetry. So conformal symmetry, I mean SL2R enhancement. So Kerr as time translation invariance, axis symmetry, and PT symmetry, and discrete flip symmetry, and the reversal of time and phi. But here the time translation is enhanced to SL2R in these two regions. And that leads to various things. But one feature that I find interesting is that there is this critical proper angular momentum that shows up. So there is a critical probe angular momentum of the probe compact object. So proper, I mean, we normalize with respect to the mass of the compact objects that rotates around it. And this angular momentum is bounded so it's, if you want to arrive to this near horizon region, you need to have angular momentum at least this value. Otherwise, you cannot arrive from the far region. So here in this diagram, you are probably not all familiar with this, but this is a depiction of this near horizon region. The horizon is here, and here is the matching region with the asymptotically flat region. Another feature using this conformal symmetry is that you can map orbits in this near horizon region between one and the other. So one example was shown here. If you have a circular orbit, so this is a constant radius in this near horizon region. You can map it to a plunging orbit in this very near horizon region, which is depicted by this small triangle here. So here it looks totally obvious because the near horizon region in this Penrose diagram is just an embedding of that one. So obviously, this curve is this one. But there's some non-trivial examples where you need to do complex transformation, and you can map orbits to other orbits just following this conformal map. And that's, you have to follow the mathematics, and you cannot see it anymore in the picture. And you also need a PT symmetry to map certain kind of orbits. So what is interesting is to look at the classes under all the symmetry group of orbits. And the only result I want to show, there is the two classes, labeled by the angular momentum. And you can map all kinds of orbits between them using conformal symmetry. And what is interesting is that in each of these conformal classes, there is a circular orbit. So if you can compute gravitational wave from circular orbit, you can apply the map, the conformal map, and then you can compute the gravitational wave for arbitrary plunging orbits. So that's the basic methods. You solve the gravitational wave emission for circular orbits by brute force. You apply the conformal transformation, and then you need to do two extra steps that I'm not going to describe really here, but you need to make an integral, and then one thing you can do is solve analytically at late times. And I'm going to skip this probably. But these integrals of this integral you have to do can be done analytically for all cases for equatorial orbits, and that's an interesting feature of this conformal symmetry. And also this kind of quasi-normal mode approximation can be done also analytically for these examples, because all the special functions that appear are just hypergeometric functions. So the final result is the one I showed you before for these equatorial orbits. And here, so it's the final Fresson result. And you have this, you find this polynomial ringing depending on the, so for this example is one particular impact parameter that is depicted here. And and then they go through the standard exponential decay. And the overall amplitude depends on the angular momentum over this critical angular momentum. And that's an interesting feature, is linear for large angular momentum, and around criticality something happens. And what happens is that you have some critical behavior, some power. So it looks like the amplitude is diverging, but actually, if you look at it more closely, the amplitude scales like here, so it was square root of lambda divided by this critical behavior. And if you go back and look at it from different perspectives, you find it in terms of the variables at infinity, it's really square root of the position of the ISCO. And so it scales like lambda to 1/3. So we have, so for the specialists here, we have a real physics of cap ADS2 where we have some strong decay that is compensated by this critical behavior, and that goes back to the scaling that I discussed earlier. And so the edge-on result, just if you want to know, has some analytic form, and it depends on these IO modes, and that's that result. So in the last couple of minutes, I would like to just discuss a couple of extensions of this. So as you know, a point particle follows a geodesic path. And there was an assumption of general relativity at the beginning, but then Einstein proved with Gromer that it's a consequence of the field equation of general relativity. But then if you consider that the particle has intrinsic spin and has a finite size, the equation changes. So it was found by Mathison Papetrou how to describe the spin, and then the theory was completed by Dixon, and the final equations are known. And these equations need to be supplemented with a condition that tells how the center of mass behaves. So there was a spin supplementary condition, and I'm not going to pronounce the author. I'm not sure how to pronounce it, but then this system is complete, and you can evolve it. So if you look at the stress tensor for such a particle, so it has the standard delta function for geodesic, and then it has a correction due to the spin, and then higher correction due to the quadrupole. So you can think of it as a hierarchy of corrections in terms of the mass ratio. So the first term is linear in the mass ratio, but then the spin correction is order q squared, skew the mass ratio. And the next order are the spin-induced quadruple corrections. For people interested in neutron stars, there are magnetic and electric tidal interactions, but for this, when you have a small mass ratio, they're very negligible. So we'll only look at the first three types of corrections. And the only result I would like to show is that you can compute explicitly these fluxes of energy radiated with the gravitational waves at the horizon and at infinity. And well, we agree with previous results by these people, and we just got the correction terms. Another extension is to look at the transition from the spiral to plunge. So that was studied by Ori and Thorne in 2000, also by Damour. So at the end of the spiral, when you are always at the minimum of your potential, at some point you can't keep up because your radiation is too strong, and then you are not at the minimum of your potential anymore, and the equation that describes your motion is not adiabatic and not circular, and you need to change your description and find what are the right equations that describe this. So that's what Ori and Thorne did with a correction due to Kesden, because the analysis was a bit flawed. And then you find a very nice match between geodesic plunge and the adiabatic in spiral. And that in that analysis, they found a remarkable equation that describes universally this transition. But it turns out that this analysis is not valid for the high spin. Terms that were neglected in the gravitational potential has to be taken into account in the high spin regime. And then if you do the analysis, you find another equation that shows up in the high spin regime, and that allows to match the in spiral to the final plunge and describe, therefore, the relevant parameters of the geodesic plunge that can be mapped to the in spiral. And then finally, we're interested in extending any kind of in spiral into this supermassive black hole. So we want to look outside also of the equatorial plane. And the important thing to notice is that, well, if we do the adiabatic in spiral, it starts from some orbits outside the black hole, and then it reaches the innermost spherical stable orbit. And if you look at what is the innermost what is it in terms of the radius here? So here I plot the radius of the innermost spherical stable orbit in terms of the angle, inclination angle. And something funny happens in the high spin regime. So here is a plot with increasing spins, and you see that in the very high spin, you reach something. So here you see that part of it is at the horizon, well, in Boyer-Lindquist coordinates. It looks like at the horizon, and part of it is not. But if you do an embedding in R2 of this spherical orbit, part of it is in this near horizon region, and part of it is not. And the boundary between the two is a funny angle that is very familiar to people working in near horizon geometry of Kerr. Is 47 degrees. So what that means is that since all this region is outside of near horizon description, the conformal methods that I described cannot apply for this kind of inclined orbits. They only apply for the ones where the zeroth order is inside of the near horizon region. And in that case, then it's possible to generalize the analysis and obtain conformal classes of orbits. And in particular, the spherical orbit is in one class, the spherical near neck orbit is in the other class. And it's also, again, possible to compute from brute force the gravitational perturbation for this, and then apply conformal maps to generate the other gravitational waveforms. So in conclusion, there is an interest for this intermediate mass ratio with high spin, but also they have a lot of very nice signatures, this fixed oscillation frequency, polynomial rigging, higher multiple emission, and special mathematical features. And such systems are ideal settings for the development of gravitational wave tools because they have a lot of simplification due to conformal symmetry. Thank you.
Thank you very much. Yes. Bringing you the
Two very quick questions. So the 1 over t behavior, this was seen in the 90s by Niels Anderson and others, right? So
yeah, so this...
you know, the sum of the quasi-normal modes going over to a tail,
yeah.
1 over t tail.
Yeah, okay, let me go to this. This one?
Yeah. So the thing is that you're showing that the sum...
So yeah, so if you know the quasi-normal modes, you know half of the answer because you need to know how you excite every quasi-normal mode with a realistic process and how it depends on the impact parameters of the thing you throw in. So this is what these plots are. So according to the various impact parameters of your compact objects, you can describe exactly what kind of polynomials you get, and you find something more complicated that is between these two, and it depends analytically on this. On this, and the formula that I show you here is an exact formula. It's really it's an exact formula at leading order in high spin, and you find this Stinch and Koch that arise from the quasi-normal mode sum, which is the sum of some hypergeometric themselves coming from analytic things. So you can track down everything.
Okay. So and the second question is, you see a suppression that goes like square root of lambda in the extreme?
Yes.
Does this match the numerics? Because there was a suppression. Well, there is a suppression in the numerics. Does it match well?
Yeah. So this square root. So the square root of lambda is enhanced with this extra critical behavior, and at the end is scales like lambda to the power 1/3. And there is a result of Gralla, Warburton, and who else? Huge, that computed with two methods. With this method, the inspiral, and found this power. And they had a standard Tokowski code, and they checked that they were matching exactly.
Do you find any new qualitative sharp features when you add the spin-spin coupling? Do you find any new sharp qualitative features to the waveforms?
Well, we were hoping to find something sharp to say, since it's a small correction, it doesn't change the leading order behavior, it just adds a small correction, so by nature it doesn't have anything sharp. But there is some sign in how this reaction comes in. So you can check the details, but there is the spin coupling has some influence. It goes in some directions, and we did not expect that especially, but it's subleading, of course.
So that form that you showed of the transition from inspiral to plunge, is that a phenomenological feat, or is it something that comes naturally from the calculation?
Yeah, we had a lot of trouble to read this literature on Orientorn. So it's you have to you take your potential and then you expand it around the ISCO, and you keep the leading order terms that are in deviation with respect to the ISCO. And then what Orientorn did is they found scaling that is consistent, self-consistent, and that allows to find this equation. But then what Kesden found is that the force velocity that they got out of this equation was negative, was not normalized. So it wasn't physical, but then it was a way to correct it consistently to keep the same equation and add some extra. Orientorn was assuming it was circular. It was still quasi-circular during the transition, and that hypothesis was proven wrong because it doesn't lead to a normalized velocity. So now we follow the same reasoning. We are expanding around the ISCO and take the near horizon. Well, they take the high spin regime of these equations, and then some parts of the potential that are that were removed by the scaling of Orientorn actually as overleading. So the scaling of Orientorn is not consistent in the high spin regime. You have to keep the other terms, and then you watch to reach another equation. That's basically.
Okay, let's move to our second speaker. Let's thank Geoffrey again. So our second speaker is Elena Giorgi from Columbia University, and she will tell us about linear stability of Reissner-Nordström spacetime.
Thank you. I would like to thank the organizer for inviting me. I apologize for the low voice. Maybe it's a good thing. I cannot talk too much. What I want to talk about is my recent work in linear stability of Reissner-Nordström black hole, maybe putting into context in the problem of mathematical general relativity of stability of black holes. So, okay, no, this does not work. I have to do this. Yeah, okay, it's better. So this is the outline of my talk. I'm going to give some motivation for the problem of stability of black holes with the Einstein equation and the Einstein-Maxwell equations. And then I'm going to state the theorem about the linear stability of Reissner-Nordström spacetime, and then give a very quick sketch of the proof, which consists basically in two parts, the decay of gauge invariant quantities and decay of gauge dependent quantities. So let's start from the beginning. General relativity, according to general relativity, a spacetime is a four-dimensional manifold equipped with a Lorentzian metric that verifies the Einstein equation, which is saying that this combination of the Ricci curvature and scalar curvature, which is the Einstein tensor, is equal to the stress energy tensor that contains all the information about the matter fields in the universe. And if you plug in T being identically 0, you take the trace of this equation, you obtain just the Einstein equation for a vacuum spacetime, which is Ricci of the metric being equal to 0. And instead, an electrovacuum spacetime would be the following, an equation that verifies the following combination. So the Ricci curvature is equal to a certain quadratic combination of a two-form, which is called the electromagnetic tensor, that verify the Maxwell equation. So this is the Einstein-Maxwell equation. So it's a coupled system of the Einstein equation with the Maxwell equation. Let's see some examples of solutions of these equations. Well, Minkowski spacetime, the spacetime of special relativity, is of course an example of a vacuum solution. A little bit more interesting is a Schwarzschild spacetime that we saw also earlier. It's a spherically symmetric spacetime, which is static, and it represents, as we all know, a black hole with mass m. So this is a one-parameter family of solutions of the Einstein vacuum equation. And now its companion is exactly the guy I'm going to talk about today, which is the Reissner-Nordström spacetime. So you see it's extremely similar to Schwarzschild, but now this coefficient, instead of having 1 minus 2m over r, he has an additional component, an additional term, plus q squared over r squared. And now this is again a spherically symmetric space-time, and now has two-parameter family m and q. And if q is different from 0, this is not a solution of the vacuum Einstein equation, it's a solution of the Einstein-Maxwell equation. So indeed, this q can be interpreted as a charge of the black hole. And of course, we also have the Kerr space-time, which has an explicit expression that I'm not writing. It's also a two-parameter family of solution of the Einstein vacuum equation. So the two parameters are the mass and the angular momentum. And if the angular momentum is equal to 0, it reduces to Schwarzschild. And there is an equivalent version in the electrovacuum case, which is called the Kerr-Newman space-time. Now it's a three-parameter family, so it has mass, charge, and angular momentum. And if the angular momentum is equal to 0, you exactly recover Reissner-Nordström space-time. So Reissner-Nordström plays the role of Schwarzschild in the Einstein-Maxwell case, as opposed to Einstein vacuum equation. Now, I told you about what's Reissner-Nordström. Now, what about stability? Well, we all know that general relativity admits a well-posed initial value formulation. This was a theorem by Choquet-Brouin in the 50s. This means that if you give me some initial data for the Einstein equation, then there exists a unique maximum development of this initial data that verifies the Einstein as well as the Einstein-Maxwell equation. So the moment I have a well-posed initial value formulation, I can talk about stability, because if I have some initial data and I know that they will evolve in a certain way. So for example, I take the initial data of Schwarzschild. I take t equals 0 in Schwarzschild. I know they're going to evolve into Schwarzschild. Then I can perturb them a little bit in some topology, in some sense, and see what happens to the evolution. And so the problem of stability is to actually understand what's happening to the evolution of this perturbed initial data. And there are many levels of difficulty that one can talk about. So one can talk about mode stability, which means you sort of decompose the solution in some modes and see if, for example, there are no exponentially growing modes. This is some form of stability. Or you can talk about orbital stability. So for example, you can actually prove that the solution remains forever close to the initial one. Or the strongest one will be asymptotic stability. You actually prove that your solution is going to converge back to the one you started with. And overall, there are two main approaches in the proof of stability, like in the literature. The first, it would be like the metric perturbation. So if you take the metric I wrote in the second slide, and you consider a variation of this metric G into a G plus delta G, you want to understand what's happening to this delta G. So that would be what metric perturbations. Or you can also perturb the curvature. That's equivalent. You can basically take Riemann curvature and consider a perturbation of it. And there have been many, many results, like in the 70s and 80s in the physics community about mode stabilities of black holes. So here are only a few names, but Schwarzschild, Reissner-Nordström, Kerr, they were analyzed both in metric perturbation, Reggie Wheeler, Wisciaswara, Zerilli, Moncrief, and also Newman-Penrose formalism, which is basically the curvature perturbation by Barden-Press, Tukowski, Chandrasekhar, Whiting. And what it was also known in the 70s is that there is a transformation theory that is now called Chandrasekhar transformation that connects these two approaches, the approach of metric perturbation into the approach of curvature perturbation. Well, it's a bit less clear what are the known results in asymptotic stability, because I just want to point out that if you have a mode stability, that doesn't even imply boundedness of the solution. If you have no exponentially growing modes, it doesn't even imply boundedness. So yes, the known results of asymptotic stability were, so the first one about the Minkowski spacetime, so the vacuum spacetime, was in the 90s by Christodoulou Kleinerman. Global nonlinear stability of Minkowski spacetime is understood and known. Then many other proofs followed. For example, one by Limlan-Reniaski in harmonic gauge. And then there was quite a jump to go to the first stability result in black holes, which is the result by Dafermo, Solzig-Roniaski in 2016 of the linear stability. So linear means you take the Einstein equation, you linearize it around Schwarzschild, and that's what they proved. And then other proofs that followed by Hankeler-Wang using metric perturbations, and then also by Johnson and Hong using two independent works using generalized harmonic gauge. And also there is a recent result by Kleinerman-Sheftel about nonlinear stability under a certain class of perturbation. Is a bit different is the case of positive cosmological constant. Much more is known because there is a much stronger decay. There's an exponential decay of solution. So the global nonlinear stability of Kerr de Sitter and Kerr-Newman de Sitter for small angular momentum is known. What I want to do, I want to continue this list and in particular focus on the case of charged black holes. So right in this list, for the first time, a black hole that has some matter on it, in particular the electromagnetic field. And so I'll just state the theorem. The theorem says that all solutions to the linearized Einstein-Maxwell equations around Reissner-Nordström spacetime with small charge arising from some regular initial data, they remain uniformly bounded on the exterior of the black hole, so they do not blow up, and they decay to some specific rates to a linearized Kerr-Newman solution after adding a pure gauge solution, which can itself also be estimated by initial data. So this is the theorem of stability, And there are two highlights in it, which are, because they are quite important. They are the two main sources of instability in the Einstein equation, which is the fact that if you perturb a static black hole, let it be Schwarzschild or Reissner-Nordström, you have to accept the fact that it can start rotating. It can start rotating and become a Kerr black hole or a Kerr-Newman black hole. So you have to allow the fact that you can decay to a slowly rotating Kerr-Newman. That's a fact of life. And also another fact of life is that if you have a solution of the Einstein equation, if you take any diffeomorphism and you pull back the metric, that's also a solution of the Einstein equation. So you have an infinite dimensional symmetry, gauge symmetry. So you have to pick a gauge to prove something, to prove decay on a certain gauge. So that's why we need to allow the choice of a gauge and the decay to not to another Reissner-Nordström, but to a Kerr-Newman solution. So are there any questions about the statement of the theorem? Okay. So then I'll try to give you what are the main steps of the proof. So as I said at the beginning, it's mainly divided in two parts. In the first part, you want to control the gauge invariant quantities. So you want to decompose your equations, find a way to find some quantities are gauge invariant, because they are going to be the ones which transport radiation. They're going to have a meaning. And this is a big part of the problem, identify gauge invariant quantities. After you identify them, you hope they verify some good equations. And then after you have these equations, you can get decay for those gauge invariant quantities. And then the second step is to control everything else. So most things are not gauge invariant, are gauge dependent. So you have to use the information about the gauge invariant quantities, use your residual gauge freedom, and identify the right Kerr-Newman parameters to prove the decay for all the gauge dependent quantities. So they're going to be this red for gauge invariant and yellow for gauge dependent to make a difference. So this is the main, what I want to stress is that you use the decay for the gauge invariant to obtain decay for the gauge dependent. But in this arrow, this small arrow, small innocent arrow, there is a huge difficulty hidden, which is the choice of gauge. If you pick the wrong gauge, nothing will work in this part. Okay. So what are the equations in Reissner-Nordström? Well, something that was known, that is known in Schwarzschild and was known in the 70s and 80s, is that the extreme curvature component of the Weyl curvature, so for those who are familiar with the Newman-Penrose formalism that correspond to the psi0 and psi4, they are gauge invariant components, and they verify what's called the Tokowski equation. And the Tokowski equation is an equation of this form. It's a box, it's the D'Alembertians of the wave equation, plus some first-order terms, so first derivative in the null directions, plus some potential. And in Schwarzschild, this was equal to 0. Now, this equation is decoupled at the linear level in Schwarzschild by everything else, which is good. But the bad thing about this equation is that it's not Lagrangian. It does not come from a Lagrangian. So the way the physicists analyzed this equation in the 70s was to decompose it in modes and to prove there are no exponentially great modes, for example. But in Reissner-Nordström, what happens here, you don't even have a 0 anymore. What you have the charge multiplied by the derivative of a certain quantity that it's defined starting from the electromagnetic tensor. So you see if Q is equal to 0, this reduces to 0 on the right-hand side. So now you have the gravitational radiation brought by alpha, which is coupled to the electromagnetic radiation as it should be. But now you want to know something about this F. You better know something about it. And in fact, what you find is that this F are also gauge invariant, and they verify also Tokowski equation that is now coupled back to alpha. So there is a back reaction between gravitational and electromagnetic radiation that interact, and there's no way of separating them. And so the breakthrough of the proof of linear stability of Schwarzschild that I mentioned earlier is that there's a way of proving decay for this quantity without decomposing in modes. I mean, like actually proving boundedness and decay. And the way is using the Chandrasekhar transformation. So in particular, there exists a Chandrasekhar transformation that brings these two equations, which are not Lagrangian, so for which all the standard techniques of hyperbolic PDE cannot be applied to obtain decay, into two well-behaved coupled wave equation. So this transformation is not trivial. I mean, it consists in taking derivatives. So you take this equation and you take two derivatives in the ingoing null direction. And so this seems like a terrible idea. If you take two derivatives of this, you're going to create lots of more terms, of more first, second, third order terms. But what happens is that they all most of them cancel out. And what you obtain is that if you define Q to be two derivatives in the going direction of alpha, and QF to be one derivative of the F, then you obtain a wave equation that does not have first order term anymore. It has some box and potential. That's it. But then it has a right-hand side. A right-hand side that depends on the other QF. And then the other equation is also coupled back to the first one. So this is the structure of the equations. At least these two equations are now Lagrangian. They come from a Lagrangian. So this is the Reggie-Wheeler equation, by the way, with a 0 on the right-hand side. Now there is no 0. There is a right-hand side. And in the case of small q, I derived combined estimates for this system, basically interpreting the right-hand side as a small perturbation of 0. And there is some subtlety in the absorption of the right-hand side in the photosphere at the trapping region. But this can be done. And the moment you obtain decay for q, by using the definition of q and qf, you can get decay for alpha and f for these two gauge invariant quantities. So this is good, but remember that alpha and f are two tensors. So if you know the Newman-Penrose formalism, they're defined as complex scalars, but they're actually the trace of a two tensor. And so being a two tensor on the sphere of Reissner-Nordström, they're supported in L greater or equal than 2 spherical harmonics. And so this means that their decay is only going to give us information about the L greater or equal than 2 spherical harmonics for all the other components. But the electromagnetic radiation is in general supported in L greater or equal than 1, because the electromagnetic tensor F is a 2 form, so the extremal component is a 1 form. So it's going to be supported in L greater or equal than 1. So part of the problem here at Reissner-Nordström is to identify a 1 tensor that transports electromagnetic radiation. And well, in Schwarzschild, you have in Newman-Penrose formalism, this phi 0 and phi 2 are the extremal component of the electromagnetic tensor. The problem, you cannot use those in Reissner-Nordström because they are not gauge invariant. So I define a mixed curvature and electromagnetic 1 tensor. So again, this is an expression of the fact that in Reissner-Nordström there is no way of separating gravitational and electromagnetic radiation. That is gauge invariant and also vanishes in Kerr-Newman. And what I computed that it verifies a Tokowski equation, which has a terrible right-hand side, like it has all Christoffel symbols, curvature terms, electromagnetic terms. But nevertheless, if you apply the Chandrasekhar transformation, so if you take one derivative of this equation, and you define P to be this first derivative, then you get a very nice Lagrangian equation equal to the divergence of the QF you had before. So now, this is very good news because, for example, you can project in L equal 1 mode. Now this is a divergence of a 2 tensor. In L equal 1 mode, it vanishes, and you have a simple scalar wave equation of this form. So you can get decay using the vector field method and so on for the L equal 1 mode. And for the L greater or equal than 2 modes, you can use a relation between those three quantities. Okay, so this means that in this way, we obtain decay for these 6 quantities that are gauge invariant. So it means that's very good news. But we still need to control all the gauge dependent. Just to give an idea, these are only few of the equations that you have in the Einstein-Maxwell equation. And everything, whatever is not red, is gauge dependent. So yeah, it's quite depressing. But what you can do, there's a way, so that's a way you can treat those. And it is some steps to control the gauge-dependent quantities. So you have to choose a gauge. So you have to start choosing a gauge. And the gauge I chose is the Bondi gauge, or the outgoing null geodesic, so the gauge that is smooth at null infinity. And then you have to make use of those two instabilities that you have. The pure gauge solution, so they're going to allow you to obtain some normalization as you wish, I mean, the ones that are going to help you, not the ones that are going to screw you. So, and I define two normalization, one as initial data, and one as a far away. So that's why far away, so very far away in the future and in space. And then you also have to identify the Kerr-Newman parameters. That's not that difficult. And then I use the initial data normalized solution to prove boundedness through integration from initial data. And then once you know that the solution is bounded, you can choose the gauge far away in this far away normalization, and they prove decay of each component through integration backward from far away. And I will only give you the picture, and this is the picture of the Penrose diagram of my black hole. So imagine that you have initial data on these two null hypersurfaces, and you can, in the boundary gauge, you can pick some gauge conditions on this null hypersurface. They will result in a system of elliptic equations to solve on this null hypersurface. And then once you have those gauge conditions, you can integrate forward to prove boundedness. And then once you know that your solution is bounded, you can go to a sphere far away in time and far away in space and construct the ingoing past null cone, and then choose gauge condition on this null cone, and then integrate backward to prove decay of the solution. So this is, you can think of this as a bounded version of null infinity. And in proving the estimates, I proved that these estimates do not depend on capital U and capital R. So basically, this is true in the whole space-time. So that's really, you can take this to be null infinity. Okay, so this is that's the sketch of the proof. You may have noticed that I said small charge. What about not small charge? Well, to understand what's the problem with not small charge, it's only at the level of the gauge invariant quantities. At the beginning, when I derived the system, I said I'm doing the estimates by absorbing the right-hand side considering it to be a small perturbation of 0. Sorry. Well, then if I want to be more careful, I have to look closer at my equation. So what I actually have, I have 3 equations. And the first 2 that I derived together, this is a box 2 because this is a 2 tensor. And then I have this one that was for a 1 form, so it's a box 1. But I also have a relation between PQ and QF. In particular, this relation is schematically of this form. So Q and QF is given as an angular derivative of P. Okay, so this means that one of these equations is redundant. Okay, so if you want to eliminate, so the way I did the estimates was like to estimate these 2 first and then this one separately. But now I have to change approach. What I have to do, I want to eliminate one of them, and I clearly want to eliminate the first one because it's the most difficult. I mean, it has a Laplacian on the right-hand side. It's like, okay, let's eliminate it. But now if I eliminate the first one, it was the equation for Q, so I have to now replace Q here. Okay, I use the relation that I have. Now this is all schematic, but what actually happens, here you have few lower order terms, they all cancel out. And this QF is going to contribute in this Laplacian that will bring back to be the real Reggie-Wheeler Laplacian potential. It's going to contribute in the potential of the Reggie-Wheeler. And this is the actual system, so the linear system of the equation. And now this angular derivative is actually, if you know, it's a D2 star operator, so it's a joint operator of the divergence on the sphere. So it means that this system is diagonalizable and symmetric, and there exists a combined stress energy tensor for the system, for which you can quite easily get boundedness of the energy for charge that are not necessarily small. And I think what's interesting is that basically I threw away the only equation that was used in Schwarzschild, which was the Reggie-Wheeler equation, and the Q quantity coming from alpha. So in Reissner-Nordström, the good quantities to consider are actually this 2 tensor and this 1 tensor that do not exist in Schwarzschild at all. So that's it. Thank you.
Thank you. If I understood correctly, the analysis was for exterior Reissner-Nordström.
Yes.
Can you say? Is there anything you can say about about stability of the Cauchy horizon and the interior?
No, it's complete different problem. Yeah, there are some results about instability of Cauchy horizon in spherical symmetry, but nothing like complete. But yeah, it's a complete different story. Yeah. I know nothing about interior.
That was beautiful, thank you. I wondered whether you think there's any hope of using the methods and the schema of the proof to transfer it to other solutions of the Einstein-Maxwell equations, or possibly say to, well, I thought in particular to the Kotler-Treff-Zweil solution, which is sort of the counterpart for Einstein-Maxwell plus cosmological constant. Would that work?
So sorry, which one in cosmological?
Kotler-Treff-Zweil. So it's Einstein-Maxwell with cosmological constant.
Which is negative. I mean cosmological. Because
I'm not sure if it has to be determined.
Because in the case of positive cosmological constant was done like 2016 by Hinz and Vasi, but for the Kerr de Sitter and Kerr-Newman de Sitter, because there you have exponential decay of the solution, so it's the analysis simplifies. And for the anti-de Sitter, for example, that's totally open. It's not even known if should be stable or unstable. So it's there are people results on it, but not of the level of the Einstein-Maxwell, but only on the scalar wave equation. It's not even complete. For other solutions, I mean, sure, I guess in general, if one has a solution of the Einstein-Maxwell equation, so whatever that would be, something like this is going to happen. So there's going to be a back reaction between gravitational and electromagnetic radiation that has to be taken into account. So it's going to be a system of wave equations, most likely. So that's in that sense, I think that this could be applied to other cases. But yeah, I don't know any specific.
Okay, thank you.
So is there any simplification that maybe you were discussing the small charge, but what happens if you go to extremality, exactly when the charge becomes proportional to the
I guess
mass?
I don't know what happens at extremality. I guess Stefanos talked about the extremal case. Many different things happen in extremal case. Even at the level of the scalar wave equation, there is a difference in behavior. So all this is a generalization of a scalar wave equation because there are tensorial wave equations with right-hand side, which are coupled together. So of course, these are like, they will have behavior that is not better than the scalar wave equation. And the scalar wave equation, we know they have, the solutions of scalar wave equation have instabilities along the horizon, as Stefanos talked about. So yeah, I guess it's not expected to be stable as a solution of the Einstein-Maxwell equation, like the extreme or Reissner-Nordström. Maybe you know more. Do you agree? Yeah, okay. So I guess it's not expected to be stable.
Okay, thank you very much, Elena.
Thank you.
So this is our last talk for today, and we are very happy to have Professor Louis Lehner from Perimeter Institute. He will tell us about challenges and some answers in the hunt for surprises in black hole spacetimes.
Well, thanks all the organizers for the invitation. I will try to, given the last talk of the day, kind of start with this challenge that has been alluded to before in previous talks, as how, given the new era that we're starting or we're living in, how we're going to go about trying to test the theory we think we have, at least for a while, to describe gravity, and how to go about and testing for surprises and what may be in the future. So of course the overarching goal would be to understand gravity in strong field regimes. And in doing so, I'm going to try to look in as many possible lampposts that I can think of. Some will be just in GR and then trying to understand what to expect there, challenge whether we actually think we know, even in the simplest regimes, as much as we should know about the theory itself. And then after I go through that, I'll try thinking, well, what happens beyond general relativity? Because after all, LIGO is doing a very, LIGO and the HT and other future efforts are going to do everything they can to try and look for deviations, because eventually we know general relativity should fail. And the deviation which should help us guide in which direction we should be looking. And what I will try to argue is that so far what we know is very limited, and the situation is rather bleak unless we start doing something rather radical. So first, let me start with general relativity as its own. So we heard from Emanuele and Michael the kind of things that LIGO is doing and what will happen, and what in the context of very high SNR measurements we may be able to do. In particular, one thing that we would like to do is understand the ring down behavior of a black hole, because we know a spectra of decays that expected for different modes. And the goal is eventually we're going to have such a high sensitivity in our detectors that we'll be able to get in a golden event every single mode or a collection of modes, and then try to test some of the most clear predictions for general relativity. But of course, another feature that we have in general relativity is that different signals of different black holes, say in the quasi-normal mode regime, are in principle mappable to any other signal. So you can imagine a standard black hole of mass, 10 solar masses and spin 0.5. You can, and in very pedestrian ways, you can take the data that corresponds to any other black hole, rescale that data to bring it back to a mass equivalent of 10 solar mass spin of 0.5 and begin stacking. So something that has been very, very successful in the context of astronomy can also be done in general relativity. And this is a paper that we put a few years ago where we're basically saying that even with LIGO, by stacking a series of events, not necessarily golding any one of them, you can actually go and after digging sub-leading signals simply by stacking. So of course, for that, we need to understand the full zoo of possibilities. How far and how long do we have to wait after, say, the merger of two black holes to the regime where this quasi-normal mode behavior is actually setting. But beyond general relativity, we want to gain insights of possible departures from relevant theories, and even the question of what a relevant theory is something that is not so clear. Of course, there are many, many options out there. Many theories have been proposed, motivated typically by cosmological arguments or by a low energy limit of some putative theories of quantum gravity. You could try and be the most conservative possible and say, I'm going to restrict of all the possible theories out there to those that have naturally second order equations, because if you have higher order derivatives, things become a royal mess. I'm going to argue later on that this might be something that we might have to go away from. But in general, an approach to try and encode possible deviations from general relativity is to think that general relativity is a part of a larger theory within an effective field theory philosophy, i.e. that the Lagrangian of your system is given by the Ricci scalar plus something else. And that something else will be corrections. And what those corrections will be is still a question mark and a matter of taste. So, but first, let's just take a step back and think general relativity. Do we know everything? Can there be surprises? And so for that, let me just look for a different lamppost. I'm going to go away from gravity, but I'm going to try to find motivations in a different corner for possible surprises. And one is in the context of anti-de Sitter, this is fluid gravity correspondence. Sorry, I'm going to be choosing the wrong sign for the cosmological constant. But in that context, there is this so-called fluid gravity correspondent that was motivated by holography. But that one tells us that, at least in that context, gravity in d+1 dimensions is dual to relativistic fluid dynamics in one lower dimensions. So once you look at the details how you derive this theory, you can ask, well, wait a minute, if this is dual, where in the world are we applying fluid dynamics to? And it turns out that that fluid dynamics is in the context of a regime that actually from a relativistic fluid dynamic consideration should go turbulent. I.e., if those two things are dual, there should be an analog to turbulence, so between quotes, in gravitational dimensions, and in gravitational theories in one extra dimension. And this is just an example of two different simulations, one carried out in the context of relativistic hydrodynamics, the other one carried out by Paul and collaborators in the context of gravity. So this was a bona fide calculations in general relativity with a negative cosmological constant in 3+1 dimensions, and this was a computation in 2+1 dimensions in hydro. And this, plus a few other insights, told us that indeed there was something interesting in the very nonlinear regime of black holes. That picture that I showed was in the context of, say, a planar black hole, something that you can find naturally in ADS. But let's forget about that for a second and think of a black hole, so a theory where the boundary is anti de Sitter, but a global anti de Sitter. So the surface is a sphere across time. And there, if you imagine what is the dual of a rotating black hole, on the boundary, what you have is a fluid that has a net rotation, and if you perturb it, turbulence kicks in, you form a whole bunch of vortices. The vortices that have similar signs, they end up joining together, forming larger vortices. They move to the poles depending on what rotation, what vorticity sign they have, and eventually they form one at the northern hemisphere and one at the southern hemisphere. This, of course, is very reminiscent of things we know. The red spot of Jupiter has a single one, and it's understood that it's formed by this process where smaller vortices that have the same side end up joining together to form a larger one. And that is a manifestation of essentially the dynamics being dominated by 2+1 fluid dynamics because the height of the atmosphere is irrelevant with respect to longitude and latitude. But very recently, so let me just give you one particular consequence of that observation in the context of gravity. So now taking it from outside, beyond anti de Sitter, we take the cosmological constant to 0 and try to say something about the asymptotic flat case. Then we did a calculation and show that in the right regime, i.e. in the regime where the quasi-neural modes decay sufficiently slowly, that non-linearities have time to do something interesting, we actually go beyond what we think, what would have naively thought the linearized calculation would have told us with respect to quasi-neural modes. So in a regime where these quasi-neural modes decay very slowly, energy can be transferred in the by nonlinear interactions, and eventually you populate a whole bunch of other modes, and you could have a potential observable consequence for gravitational wave measurement. So as opposed to us turning a detector and thinking that the main signal will come in the L2, M2 modes, this could end up being a collection of L's and M going all the way to 1, which is the analog of these two dual vortices that are going around on the sphere. Recently, however, oops, there was another plot here that got lost. Anyways, so recently, however, the Juno spacecraft went by Jupiter, took a picture of both the North and South Pole, and lo and behold, there were several vortices there. People call this a vortex crystal, or a crystal vortex. And this goes against what I just said, where vortices of the same sign are supposed to join and form a larger one. There is still quite a bit of debate of what's going on in here. One understanding is possibly Rossby waves are preventing these vortices that otherwise would be joining through differential behavior on the net amount of rotation around the pole from merging, and then this is how this structure gets created. But again, this begs the question, does this happen in the context of the fluid gravity correspondence? And this is a simulation that we recently have done of the dual fluid of a Kerr ADS black hole in the right regime. And again, these kind of structures do form. So this is possible, again, surprise that may arise purely in general relativity that we might have to be concerned with. So let me now move beyond GR. That was a bit of a crazy thought, but let me just say, well, let's suppose we know everything we can know about general relativity. I just told you that even we can, with the right assumptions and the right stacking of events, we can dig deeper within GR. But what happens if we do that analysis and we end up having a result that is different from the one in general relativity? How are we going to analyze the results we obtain, not only as to understand yes, there is a deviation, but also what is that deviation telling us? What is the indication in which direction should we be thinking about modifying the theory? So there are many alternatives, as I said, of people have been written possible extensions of general relativity. These are motivated by further physics, i.e. adding, considering fields beyond just a gravitational tensor, trying to break some well-loved symmetries like Lorentz invariance, equivalence principle, etc. And as I said, in general, if you think of these modifications as within an effective field theory consideration where GR is just a leading term, you say, well, my theory would be GR plus some corrections, and these corrections will be coupled, will be modulated by some coupling strength. And there is in principle no reason to expect that this coupling strength will be much different from the Planck length or a Planck mass. However, there are arguments to say, well, if things are no local in some sense, this coupling might be a lot stronger. And so at the very least, given that we have a new set of observations, we should just go and then try to measure as much as possible. And at the end, at best, we might end up putting a constraint on these possible modifications. The problem, as I said, is that there are too many options. If we're going to be studying every single theory that is out there, we will never finish. So at least what I want to do now is to try and think, what is the program that those that love a particular theory should follow in order to have, at the end of the day, some particular information that LIGO and other efforts could use. So I'm going to go from the simplest case and then try to illustrate how the number of difficulties that one has to face. So beyond general relativity, perhaps the easiest possible set of theories that are out there are these theories called scalar vector tensor theories, which are described by something like so. There is an extra field called sometimes a dilaton field, and that in the right regime gives you some very interesting phenomenology that has been understood in the context of binary neutron stars and black hole neutron stars. Unfortunately, in the case of binary black holes, they're very mundane. They produce nothing different from general relativity unless you come out and drop in here some potential that has been, in some sense, engineered for things to happen. Naturally, I would argue there is no reason for binary black holes in this type of theories to give any difference. These theories are part of a much larger family of theories called the Hordensky theories of gravity, which are the most general type of theories that will give you, at the end of the day, second-order equations, which, as I said, is important to guarantee that your system, your problem will be well posed using also the same expression that Elena used. You want a theory that guarantees you're going to be able to find solution. Those solutions will be unique, and they will be continuously dependent with respect to whatever initial data you chose. So if you chose a slightly different initial data, but very close by, you expect a solution that will not be too different from the other one in some mathematical, well-understood way. So these theories have been understood and been applied in the context of cosmology a lot, especially, for instance, if you look at this term, r plus x, if x happen to have the right sign, i.e. a positive sign, this looks like a cosmological constant. So it's a natural way of incorporating within a dynamical theory lambda. So typically, studies within these theories have been done on the linearized regime. The question that we have at our hands is we're studying systems that are strongly nonlinear, so we cannot rely on a linear approximation with respect to, just say, Minkowski. And we want to understand where these theories have a well-defined initial boundary value problem. Very recently, so people for a long time, you see this is a whole mess. People have stayed away from that, but very recently, bold and courageous people have gotten into that, and in particular, Papaleo and Real have recently concluded a very, very small subset of the theory has a well-defined initial value problem in the linearized regime. Of course, people on the other side, especially in cosmology, push back saying, well, wait a minute, the proof relies on having chosen a very special gauge, so maybe that's just an artifact of the gauge that was chosen. So together with a postdoc and a student, we took a look at that subset of theories that Papaleo and Real argue is the only one that can survive. But instead of analyzing in the way they did it, we take a conformal transformation, and this is just too messy an expression, but the only thing I want to point out is that, notice this is the equation of motion that determines Einstein's equations. So we have second derivatives here of the metric tensor, but not second derivatives of anything else. However, the equation of motion for the scalar field has second derivatives of the scalar field itself. So you can rewrite this by saying the metric obeys a similar equation that you would have had already in Einstein's theory, but a scalar field obeys a slightly different equation of motion that involves gradients of the field itself. And this is a royal mess, but at least in some cases you can say something. In the weak field case, in the weak data case, you can argue using Kleinerman's null conditions plus something about Strauss conditions on the potential that you would be able to guarantee global well-behaved solutions. But in the nonlinear regime, things can happen. So if I look at this equation, because it has gradients here, you can see that as the gradients grow, you may actually end up changing the signature of this matrix here. And your hyperbolic problem might turn into parabolic and elliptic. So there could be a strong impediment on being able to actually look or ask for long behavior of these equations, of these theories. So I'm not going to give you anything but that. What I can tell you is that the paper has been put just a few weeks ago, and indeed what we confirm is that weak data, in the case of weak data, all is good, but in the case of strong data, you actually indeed find this changing character of the equations, and things break even before you would have thought things could have broken from an EFT point of view. So the systems go bad, the equations go bad, even before otherwise with some simple arguments you would have expected. So my argument is, well, careful, there might be a no-go there as far as trying to use them, as advertised for a nonlinear study of these theories in the context of, say, binary black hole collisions. However, if you are from the other side, a proponent of one of these type of systems, you will tell me, no, wait a minute, you're pushing too hard here. I told you this is to be thought of as an EFT argument. I gave you the leading order correction to the Einstein term. What you're supposed to think is further terms will come and keep correcting things. But if this is the case, you will generically have higher order contributions, which will bring higher order gradients, and then will create worse problems. So we're kind of caught in some catch-22. We want to make progress, but it seems that the direction to make progress is to get into a worse scenario than we started with. So let me just give you one random example. This is just one theory picked out of many. So this is called dynamical Chern-Simons, where the equations of motion are given by this, but this tensor here has, in particular, derivatives of your Riemann or of your Ricci. So this is an equation, this will give you an equation of motion to have second and third derivatives. So, I mean, I cannot, there are many other things that are uglier than this, but this is ugly enough for me. So, but how do you want to make progress with them? That was just an example, but in general, there are many theories out there motivated, often involving curvature corrections, which may or may not have extra degrees of freedom and non-localities. So how are we to make progress on there? Because after all, in these theories, or in some of the theories, people have found black hole solutions, and they are asking questions like, how would the image of M87 will change if that black hole was to be governed by one of these solutions? Well, we need to know whether those black holes naturally present in this theory are different from those in GR, where they are stable, because it would make no sense for me to think of a theory that gives me a black hole that is unstable to even begin studying them. Why would I waste time trying to create images given that they are already so expensive to come up with? We would need to understand their dynamical behavior. After all, we would be thinking what would be the typical signal of a collision of two black holes in this theory. And how would they relax to equilibrium? Do they do so, or do they take in a similar way to general relativity, or do they give a very significant behavior that will allow us to put significant constraint on them? So the question is, how do we probe what could take place given these motivations? And of course, in the back of our minds, we always want to use the evidence from the data to tell us what should be the ultimate theory that we should perhaps be trying to write. So there is, the picture that we have in our mind is that there is an underlying theory that no one has written yet. Some EFT, some truncation gives us the theories that we have been presented with. But these are full of pathologies from a mathematical point of view, which are exacerbated by the numerics, but has nothing to do with the numerics themselves. On their own right, at the mathematical level, they have tons of problems to make progress. So we need somehow to fix them. And hopefully this fixed version not only will inform us of something about the truncation theory, but importantly, as to how this underlying theory should behave. So the strategies that people are pursuing are typically along the following line. It's to say, well, there is something called reduction of order that has been very successful, say, in particle physics, where you say, well, first solve your solution as if it didn't have these higher order correction terms, and then plug that solution into the right-hand side that has the correcting term and iterate. And hopefully, everything will make sense. There are other possibilities. One is to modify the equations of motion. You take the equations of motion as you had them before, you put the right-hand side, but then endow the equations or the system you have with a new equation, which governs the evolution of the right-hand side, such that asymptotically, with a new scale in the program, this f converges to the source, and then as a result, you end up having a theory that is faithful to the original one. This you might not be familiar with, but this is something that has been known for a while in the context of relativistic hydrodynamics, so I'm going to hydro again. In the context of relativistic hydrodynamics, the moment you introduce viscosity, the equations of motion stop making sense. There is acausal propagation, and the solutions will be wildly violent. So Israel and Stewart, some decades ago, proposed exactly the kind of idea I just described. If you have the stress energy tensor of your space-time will be given by something which is a perfect fluid, of which the divergence give you equations of motion that are perfectly well behaved. But if you have gradient terms coming from viscous contributions, then as well define a new quantity which contains all the gradient terms and impose on that quantity a new evolution equations that will guarantee that the effective field theory description, that the higher gradients are subleading to the lower ones, stay put. So mathematically, this guarantees now that the equations will be well behaved, but physically it's a completely different matter. For instance, in the example I told you about of hydrodynamics in 2 dimensions, where vortices actually, instead of breaking into smaller and smaller ones, i.e. giving you larger gradients, they join, therefore giving you slower and lower gradients. In 2 + 1, this theory is perfectly well behaved. It doesn't really change the physics. The moment you apply it in 3 + 1, you're really beginning to mess up with the physics, but that's the only way to make progress in some sense. And this is being used, for instance, to analyze the quark-gluon plasma in collisions at the LHC. So I'm going to take a very simple and mundane example just to illustrate how would this work and all these difficulties. Suppose you start with these models. This is a model of 2 scalar fields that are interacting with each other and there is a potential. If you analyze the equations of motions of this problem, you have 2 equations that are perfectly well behaved. So there are 2 wave equations for the field rho and the field theta with some coupling. But the field rho feels this potential. So one approach that you could choose is to iterate out this rho field and plug the solution back into the action. And what you find is now this equation, which is this action, which is only an action for the field theta, but now you have many more derivatives. And if you actually ask for what the equations of motions of this is, it's given by that. So all of a sudden you have an equation of motion that is no longer the wave equation, and sorry, here theta became phi. That's just picking things from 2 different papers, but it's the same. So the action of this action changed theta to phi gives you these equations. And here you see much higher derivatives. Here's a box, 2 derivatives more. This is a royal mess again. But the good thing is that we have the original problem, and we can solve this. This will be the analog of getting the solutions of the true problem that we want to solve. This is a luxury that typically we don't have. This is the EFT set of equations, and we can ask, given the strategies that I have put forward, how do they work? So the option 1 would be to use the reduction of order. The option 2 would be to use this one where we modify the right-hand side to include all this, and with an ad hoc equation to ensure that higher order gradients stay subleading. And okay, this is an example where the coupling is weak, so these extra terms are not having a strong leverage in the problem, and by and large, the solutions in both cases agree, and what we're doing here is computing the error with respect to the full solution that we can obtain in this case. We increase the coupling a little bit, and the reduction of order method doesn't work anymore, while this kind of correcting of the equations at Israel Stewart let us keep going. So the conclusion we draw from is that the option 1 is delicate. For small enough coupling, it gives you a way to get obtain some feeling of what the solution should be. The option 2, it seems fine, much more robust in general. But first, you have to justify it. I said, here what you're doing is just forcing the system to guarantee that the higher order gradients stay put. Who tells us that we have the right to do that? What I would argue is that LIGO and Virgo has already given us that luxury. We go and see the waveforms that LIGO have obtained, especially the first one that was so strong that we didn't even have to use a template to dig it out. And we already saw these two black holes coming together. The wavelengths stay put. And we saw the merger, and we saw the deviations from generativity are not very strong. So that's telling me that whatever correcting terms are there in whatever EFT you may think of are not significantly affecting things, or they're not growing in any way in a wild manner. So what we have to do is just come up with the best theory we can and control the nuisance that are there on the mathematical level that are preventing us asking the questions on the nonlinear regime. So there seems to be a way to avoid not going to a nonlinear land. Typically, this is what people have been doing because of the pathologies that one sees at first sight, and perhaps ask through a fixed version. We're proposing this particular method to ask questions of your theory and get insights of how the true underlying theory should behave. So just to wrap up, it's obviously the case that we're living exciting times with respect to black hole research. We have plenty of ways to go into the data. We know, of course, that the deeper we go into the data, the more physics we can extract. There are riskier strategies, for instance, stacking signals that could be well understood, under control, and let us ask much more strenuous questions to the data. We are at a regime where there is limited knowledge so far of what else might be out there. And the important thing of this what else is not only to help LIGO dig deeper in the data, but also at the extent or in the event that we do see departures to try and infer what is that telling us about nature. And I think we are homing in on options to try and ask questions in the right regimes of many putative theories that try to extend generativity. And hopefully, if you like one of those theories and you want to ask the right questions, then there is a way, there's in some sense, a cleaner path forward to make progress in this regime. Thank you.
So I usually advocate listening to experiments, having a dialogue with nature. But in this case, I would like to advocate actually Einstein's approach of thought experiments, because it seems to me that Einstein's theory tells us that it really breaks down at the singularity. It doesn't break down at the horizon. And there are two singularities we know. One is the Big Bang, and the other one is in black holes. And presumably, once we solve one of them, we will solve also the other. And so if I had to devise a strategy, my approach would be, let's try to cure those singularities first. And so don't worry about what LIGO would see, because that probably is not at the Planck scale, so we will not see any quantum effects. That's the most sensible thing to assume. I mean, I don't think, that's the most conservative approach. And then let's just focus where Einstein's theory breaks down. Not where LIGO looks, but where the theory tells us that it breaks down. Listen to that, and try to think how to cure that. And so any solution we find for the Big Bang singularity, and there are suggested solutions, should apply also to black hole singularity. So what is not clear to me is why aren't, for example, string theories focusing on the singularity of black holes, trying to cure them? Or why isn't anyone that tries to imagine an extension of Einstein's theory focusing on the singularity? Why are we dealing with the horizon?
Great, that's a very broad question. We can have 2 talks on just on the first and the second part of that. So let me just argue. So first, I think I'm with you there. I do think that, well, that's a true place where the theory is breaking down. But we also know, just to try and advocate kind of the opposite way or on the other side, that we have dark matter, that we have dark energy. We have 95% of the stuff in the universe we have no clue about. It could be on the right-hand side or it could be on the left-hand side. It's very, very uncomfortable, even just the answer of what the cosmological constant being a constant that came out of nowhere be, even though it makes perfect sense if we are trying to use it in kind of in the astrophysical context. That would be one. The second one is the assumption, and it's a natural assumption to say, well, it's at the singularity where things break down with respect to generativity, but what if, and it's a natural thing to think, that there are corrections that are there that come with curvature, natural scaling just based on curvature. So from this point of view, I don't think, and sorry for saying the following, I don't think the EHC has a chance of seeing a departure of generativity if the corrections come with respect to curvature. If they come with respect to the non-local structure on the horizon, then, well, of course, they're and as much as a game as LIGO itself. But why not look, right? I think that given that the data is there, it would be a disservice for it not to have some people doing it. And given that there are some people that are writing down theories, what I'm saying is, okay, I'm not going to go there, but I'm telling you how you could, and people should.
You said at some point that scalar tensor theories basically give the same picture of binary black holes as GR. But wouldn't the gravitational waves they emit potentially look different, given that there's an extra polarization degree of gravitational waves in scalar tensor theories?
Yeah, so let me just, and thanks for the question, because I will clarify something. So scalar tensor theories, in the context of, say, at least one star in the program, will turn on all its possible phenomenology, extrapolarizations, phase transitions, etc. The problem is that unless you, from God-given or by hand, you put a potential that forces black holes to turn on this effect, or you have a background cosmological constant that is not constant anymore, but now it varies with time, they do nothing with black holes. So a black hole cannot support the hair, and as a result, the solutions of for black holes in the context of scalar tensor theory are the same ones as those in generativity. So this violation of the equivalence principle that they naturally have, it doesn't apply to the case of just binary black holes. Of course, you can do plenty with those theories and put very nice constraints like the binary pulsar has done, and also LIGO is going after. And they can do also, in some sense, stronger tests within these theories in the context of at least having one matter source. But if not, it's harder.
Okay. Thank you.
Okay, if there is no more question, let's thank Luis again and all the speakers for today.